A trillionth of a second after the beginning, the entire observable universe was smaller than a grain of sand. 10 to the power of a Google years from now, it may be a thin, cold haze of photons drifting through almost perfect darkness. And the strangest part is not the scale. The strangest part is that physicists can now sketch both of those moments with terrifying precision. Not perfectly, not confidently about every detail, but from about 10⁻43 seconds after time, switched on, all the way to a future so distant you would need more zeros than atoms in your coffee mug to write it down. We have a timeline, a script for everything, from the first quantum flicker of space-time foam to the last black hole evaporating into a whisper of radiation, to a universe that may just sit there forever, frozen, doing no more useful computation at all. Here is the thing. That script might start with nothing. Not empty space, not a quiet void. Literally no space-time, no before, no after. Then a quantum fluctuation, a tiny, lawless blip in a sea of no laws, inflates into all of this. In a sense, it was the ultimate free lunch. And the same vacuum that gave you galaxies, stars, and the chair you are sitting on could, according to some calculations, one day flip again and erase everything at the speed of light. If a more stable vacuum bubble ever appears, it will not politely schedule a press conference. It will just expand, faster than any warning signal, rewriting the laws of physics as it goes. One moment you are watching a video, the next moment there is no you, no video, no classical reality to complain about the result. Let that sit for a moment. Now project forward. Not to your grandchildren, to your great-great-grandchildren's great-great-grandchildren, living tens of billions of years from now. The sun is gone. The Milky Way and Andromeda have long since merged into a swollen elliptical galaxy under a black sky. The universe is dimmer, colder, more fragile than the one you woke up in this morning. And yet, by our best models, it is still barely out of cosmic childhood. Some physicists look at this timeline and say, this cannot be the whole story. Sean Carroll talks about an infinite multiverse where our Big Bang is just one branch in a vast quantum wave function, a tiny local fluctuation in an endless sea. Roger Penrose imagines a cyclic universe where the heat death of one cosmos becomes the Big Bang of the next, erasing clocks but preserving patterns. Elegant ideas, all incomplete, none fully satisfying, because buried inside this timeline is a deeper mystery. If time itself has a beginning and very likely an end, what does that make of our razor-thin moment in the middle? And what exactly is doing the computing that turns quantum chaos into a structured universe with stars, chemistry, and you, right now, asking how the story ends? We will get to that. Welcome to the end of the world, but not yet. So let that sit for a moment. You and I are about to walk from the first flicker of time the equations can even talk about, all the way to the last shiver of a universe that may be so thin and cold that even the word nothing feels too crowded. That is a lot to ask your brain to hold at once. So this is not a quiz. This is a late-night story. If you are new here, this channel is where we take the wildest ideas in physics and cosmology and treat them the way they deserve to be treated, as suspense stories about reality itself, not as dry lectures, not as a wall of equations. We talk about quantum fields, black holes, and the end of time the way you would talk about a mystery that has been running for 13.8 billion years and still has not revealed the final twist. Here is the thing. The universe is already impossibly dramatic. You do not need me to add jump cuts and fake tension. The Planck era, at 10⁻43 seconds, is a regime where space-time is foaming, where our best theories just stop. Inflation takes that quantum chaos and blows it up faster than any machine you have ever heard of. Stars ignite, galaxies collide, black holes compute the entropy of whole regions of space. The only real job here is to slow the story down enough that you can feel the difference between those moments. So, pour yourself something warm. Dim the lights if you can. If you are watching this on a phone, maybe set it down next to you. and just listen for a while. We are going to drift from 10 to 43 seconds after the beginning, through the first atoms and the first stars, past the death of our sun in 5 billion years, and out into a future where the last black hole evaporates somewhere after 100 years. In a sense, it was inevitable that we would try to tell this entire arc in one sitting. The universe has been rehearsing it for a very long time. And the strangest part is, this is meant to be comforting. Because when you see the whole timeline, that razor-thin human moment in the middle stops feeling like a random glitch and starts to look like a particular kind of computation the cosmos is running on itself. If you enjoy having your sense of reality gently destabilized, if you want more long cinematic dives into quantum foundations, dark energy, and why there is anything instead of nothing, then you might want to hit like and subscribe. Not because an algorithm demands it, but because this is an ongoing story, and the next chapters are already queued. I will guide you through this at a deliberate pace. We will start painfully slow, inside the first fractions of a second, where every 0.0001 matters. Then we will accelerate. Billions of years will pass in a sentence. Later, as the last stars fade and black holes whisper their final hawking photons into the dark, we will slow down again, because those quiet, stretched out ages at the end of time might contain the most unsettling implication of all. We will get to that. How this story unfolds. From first flicker to final silence. So here is the thing. That wild zoom we are about to do is not just a tour of trivia. It is a single, continuous story, from the first quantum flicker of space-time to the last whisper of energy in a frozen void. And the strangest part is that your entire life is wedged into a vanishingly thin slice of that timeline. We are going to run this like a 3-act play. Act 1 is the rise. How a universe that may have begun as a near-nothing quantum fluctuation, an unstable, almost vacuum, inflated, cooled, and condensed into atoms, stars, galaxies, planets, and eventually, beings like you who can ask, what on earth is going on? In a sense, it was the longest origin story ever told, and we will walk it from the Planck time, 10:43 seconds after the beginning, out to the first galaxies lighting up the dark. Act 2 is the dismantling. Every structure that forms fails. Stars burn through their fuel, galaxies collide and fade, black holes feed and then evaporate. We will watch the sun swell into a red giant in 5 billion years, the last star in the universe flicker out trillions of years after that, and the great machines of gravity and nuclear fusion wind down into silence. Then we push even further, into the black hole era and beyond, to the thin, cold radiation of a near-empty cosmos. Act 3 is where the physics starts interrogating meaning. Once we have the whole arc laid out, we will ask what it implies about reality itself, whether time is a fundamental ingredient, or just a pattern that the underlying code of the universe runs for a while and then stops. If you are new here, pour yourself something warm, because that is where the existential vertigo really kicks in. To make any of this feel human, we will keep changing the zoom level. One moment we are talking about Planck scale foam, distances so small that a proton looks like a galaxy. The next, we are jumping to 100 years in the future. To keep your brain from melting, we will keep coming back to a 24-hour cosmic clock. Midnight is the beginning. Now is a split second before the end of the day. Human history? That is the last fraction of a second before midnight strikes. And here is the uncomfortable result. Every breath you take depends on a very specific, temporary window in that day. Too early, and the universe is a hot plasma, no atoms, no chemistry, no lungs. Too late, and the stars are dead. The temperature has fallen, and there is no free energy left to drive metabolism or thought. You live in the narrow gap between too chaotic and too dead. So we will not only follow the mainstream forecast, heat death, a universe that thins out into uniform, useless radiation, but also the weirder branches of the decision tree. What if dark energy grows and rips apart galaxies, stars, even atoms in a final big rip? What if our vacuum is only metastable, and at any moment a bubble of lower energy reality could nucleate and erase everything at the speed of light? What if there is no single beginning or end at all, just cycles, or universes budding off universes, or a deeper machine in which our entire timeline is one temporary computation? By the end, when we have run the clock all the way forward and then stepped outside it, we will circle back to the question hiding underneath all the equations. If time itself is just a pattern the universe is executing, what does it mean to be a conscious process running inside that pattern right now? Let that sit for a moment, because in the next section, we start the clock at 0 and press play. Part Y, Before Time, had a name, the Planck Era. Part 1, The Age Before Laws. We are not just winding the clock back to the Big Bang. We are stepping into a region where the very idea of a clock stops making sense. This is the Planck Era, the briefest, wildest chapter in our entire story. And the strangest part is that our two best machines for understanding reality flatly refuse to agree about it. On one side, you have general relativity, the smooth classical theory that treats space-time like a continuous fabric. On the other, you have quantum mechanics, the rulebook for the jittery, probabilistic microworld. Everywhere else in the universe, we juggle both and get away with it. Here at the beginning, they collide. They do not merely give different answers, they ask incompatible questions. Physicists draw a line in the sand. Planck time, about 10 to the minus 43 seconds after t bar 0. Not a millionth of a second, not a trillionth, but a decimal point followed by 42 zeros and then a 1. Let that sit for a moment. That is the earliest instant at which our current equations even pretend to say anything. Before that, the symbols on the page turn into nonsense. There is a matching distance scale, the Planck length, around 10 to the minus 35 meters. If you shrank yourself down until the entire observable universe was compressed to the size of a coffee cup, the Planck length would still be unimaginably smaller than a single atom in that cup. Below that, here, and there, stop being well-defined locations. Space itself loses its job description. Here is the thing. At these scales, you cannot ignore quantum effects of gravity, and you cannot ignore curvature. And when you try to write down both at once, the computation explodes. The result is what people call quantum foam. Not a smooth stage where matter acts out a play, but a seething, flickering sea of microscopic bubbles of space-time, constantly appearing and annihilating. In a sense, it was like boiling water, except the thing boiling is geometry. In that foam, the difference between space, time, and energy blurs. Are you looking at a tiny loop of warped space-time? A transient particle? A fluctuation of the gravitational field? At that scale, the universe refuses to tell you. If you are new here, this is the point where you realize the phrase, "before the Big Bang," is not just forbidden by data, it is forbidden by language. So when cosmologists talk about the beginning, they usually mean after the Planck era, after the foam calms just enough that we can pretend space-time is a smooth backdrop and run our equations forward. Our timeline starts not at the first instant, but at the first moment our laws stop screaming. Pattern interrupt. That means whatever set the initial conditions for everything that followed may not live inside space, or time, or matter at all. If the machine we call the universe is running on something deeper than space-time, what exactly are we living inside now? We will get to that, but first we have to watch the foam freeze into a universe we can actually recognize. When nothing exploded, quantum fluctuations and false vacuum. So when the foam freezes, it does not freeze into a clean, empty stage waiting for actors. It freezes into something much weirder, a quantum vacuum. And here is the thing. In modern physics, vacuum does not mean an empty box with nothing inside. It means the lowest energy state of a field, the ground floor of reality itself. You can think of it as the universe with the lights turned down as far as they can go. No stars, no atoms, no classical objects at all. But even then, the quantum fields that make up everything are still there, humming. They are never exactly zero. They fluctuate. For a brief moment, a particle-antiparticle pair can appear, borrow a little energy, and then annihilate before the universe notices the debt. Let that sit for a moment. Even nothing is doing frantic bookkeeping. If you are new here, this is where the story stops feeling intuitive. Because in quantum field theory, those fluctuations are not a glitch. They are the default. The vacuum is a machine that never turns off. The result is a seething sea of temporary excitations, a constant foam of almost real particles popping in and out of existence too fast for classical detectors to track. Now add one more twist. Sometimes what looks like the lowest energy state is not truly the bottom. It is a false vacuum, a metastable state perched on a plateau of potential energy. In a sense, it was nothing, but only in the same way a ball perfectly balanced on a hilltop is at rest. It is quiet, but it is not safe. Picture a perfectly still pond. From a distance, the surface looks smooth, calm, featureless. Under a microscope, though, you see tiny ripples, thermal jitters, microscopic waves colliding and cancelling. Now imagine that one of those tiny waves, just by chance, grows instead of shrinking, rises instead of fading, and suddenly triggers a tsunami that tears open the shoreline and floods a whole new basin. That new basin is not just another wave, it is a new ocean. Translate that back into physics, and you get the wild idea. A tiny quantum fluctuation in a false vacuum can nucleate a bubble where the field finally rolls down to a true minimum. Inside that bubble, the stored potential energy converts into a violent burst of expansion and radiation. Space itself stretches. Time acquires a direction. Fields settle into new values. The computation we call a universe boots up with its own space-time, its own constants, its own rules. And the strangest part is not that this might have happened once. The strangest part is that in many models, a false vacuum does not pop a single bubble and stop. It keeps inflating, keeps fluctuating, keeps spawning bubbles forever, which raises a question you cannot unhear. If our cosmos is just one stabilized bubble in a larger quantum vacuum, how many other bubbles are out there right now, forever beyond our reach, writing their own histories while we pretend we are the whole story? The inflationary firestorm, how space itself went supersonic. So our universe is just one bubble in a larger quantum froth. But here is the thing. Our bubble did not just drift gently into being. It detonated. For a brief, ridiculous moment, space itself went into overdrive, ballooning faster than any explosion you have ever imagined, turning a subatomic speck into something already on its way to becoming a cosmos. This phase has a name that sounds almost modest: inflation. Do not let the word fool you. We are talking about space doubling in size, not once, not twice, but again and again and again in less than a trillionth of a second. An exponential runaway driven by a peculiar energy field we call the inflaton, or a false vacuum, whose favorite hobby was stretching reality. Now, that immediately raises a red flag. Faster than light. Isn't that impossible? Here is where you have to be careful about the rules of the game. Nothing is allowed to move through space faster than light. But during inflation, nothing had to. The fabric of space between points stretched, and as it did, distant regions receded from each other faster than any signal can travel. No law was broken, because the racetrack itself was expanding under the runner's feet. Let that sit for a moment. In your everyday classical experience, motion means objects changing position on a fixed stage. During inflation, the stage itself was the machine doing the motion, silently pulling every mark on the ruler away from every other mark. That is the difference. The speed limit applies to actors in space-time, not to space-time reshaping its own geometry. Why invent such a wild story? Because without it, our observable universe makes no sense. Look at opposite sides of the sky. They are almost the same temperature to 1 part in 100,000. Yet, given the finite speed of light, those regions were never in contact in a simple Big Bang model. That is the horizon problem. Inflation solves it in one stroke. All those regions were once crammed into a tiny well-mixed patch, then blown apart. The flatness problem is the sequel. Measurements show our universe is astonishingly close to geometrically flat, like a sheet of paper rather than a closed sphere or an open saddle. That flatness is unstable. Any tiny early deviation should have grown. Inflation acts like a cosmic ironing machine, stretching space so violently that any initial curvature is flattened out, leaving the large-scale geometry we see now. And the strangest part is not the speed. The strangest part is that quantum jitter during inflation did not get erased by all that stretching. It got magnified. Tiny fluctuations in the inflaton field, microscopic variations in energy density, were dragged from subatomic scales to cosmic scales. Those ripples in the early plasma became the seeds of galaxies, clusters, and the vast cosmic web. In a sense, it was quantum randomness doing urban planning for the entire universe. We will get to the observational proof, but you already know its name. The cosmic microwave background is our baby picture, a faint, frozen glow from about 380,000 years after the beginning, still carrying the imprint of those stretched quantum ripples. In the next section, we are going to read that pattern like a forensic report and see just how much of our fate was written in the static. Echoes of the first light, the cosmic microwave background. You can actually see the afterglow of the beginning, not in a philosophy book, not in a simulation, but as real photons hitting real detectors right now. Astronomers call it the cosmic microwave background, the CMB, and here is the thing. This is fossil light. It comes from a moment about 380,000 years after the Big Bang, when the universe finally calmed down enough for something very boring and very revolutionary to happen. Electrons and protons paired up into neutral hydrogen atoms. That sounds like a minor chemistry update. In a sense, it was. In reality, it changed everything. Before that transition, the universe was not a peaceful black sky. It was more like the inside of a star had been scaled up to cosmic size. A hot, dense plasma, electrons and protons flying around, light bouncing off charged particles every fraction of a nanosecond. Any photon trying to cross space was immediately scattered, again and again, trapped in a chaotic pinball machine of quantum interactions. So when we talk about looking back earlier than 380,000 years, there is a hard limit. The universe was opaque. There was no clear line of sight, just a glowing fog. From our perspective, that fog is the wall of the observable past. And the strangest part is, we are not guessing this from pure theory. We have actually measured the glow from that wall. As expansion stretched space and cooled the plasma, the average energy dropped. Once it slipped below a critical threshold, electrons could finally stay bound to protons. The fog lifted. Suddenly, photons were free. The light that had been trapped for hundreds of thousands of years was released in all directions at once. Those same photons have been traveling ever since, while the universe expanded by a factor of about 1,000, stretching their wavelengths from fierce, white-hot glare down into microwaves. Let that sit for a moment. Every patch of sky, every direction you point an antenna, there is this faint hiss at about 2.7 degrees above absolute zero. That is not instrument noise. That is the thermal echo of the universe's childhood. Now here is where the earlier story about quantum fluctuations cashes out as data. The CMB is not perfectly smooth. When satellites like WMAP and Planck mapped it, they found tiny temperature variations, differences of about 1 part in 100,000. Hotter spots, cooler spots, arranged in a very particular pattern. Stop and really look at that famous false color oval map for a second. If you are new here, it probably reads as science wallpaper. but reframe it. That is not a diagram. That is the oldest photograph in existence. A baby picture of everything. Those tiny blotches are the inflation-stretched quantum ripples, frozen into matter and light. Slightly denser regions pulled in more material. Gravity amplified the gaps, and over billions of years, those almost imperceptible temperature differences became galaxies, clusters, and eventually you sitting there asking what reality is. Pour yourself something warm and think about the implication. From that one sky-wide image, we can infer the universe's age, its composition, even the amount of dark matter and dark energy. This is not just a pretty result. It is a forensic report on the entire cosmic machine. And yet, the CMB is only the opening snapshot. In the next section, we will fast forward from that baby picture into the turbulent adolescence of the universe, when the first stars ignited and darkness was broken for the first time. From plasma to particles, the first second of everything. If the cosmic microwave background is the baby picture, the first second is the delivery room, and the cameras almost missed it. Everything that will ever happen is compressed into that blink, and the strangest part is how much structure gets locked in before there are even atoms, let alone galaxies. So, rewind, way past the CMB, way past the first atoms, we drop into the universe when it is less than a trillionth of a second old. At around 10 or 12 seconds, temperatures are so high that what you and I call matter is just a rumor. Quarks, leptons, photons, neutrinos, all tangled in a quantum storm. The forces you learned in school are not separate yet. Electromagnetism and the weak nuclear force are still fused into one electro-weak interaction. Here is the thing. This isn't just hot. This is, every cubic centimeter holds more energy than all human technology ever will. Hot. In that furnace, symmetry rules. Particles are massless, racing at light speed. The universe is a machine with no moving parts because there is no meaningful way to tell one part from another. Then, a phase transition. Around that 10-12 second mark, the Higgs field, which had been hovering near zero, suddenly settles into a non-zero value. In a sense, it was like steam condensing into water, except the liquid, now filling all of space, is a field that tells particles how heavy they are allowed to be. Electromagnetism and the weak force split. W and Z bosons become massive. Electrons and quarks pick up mass. The rules of classical reality start to emerge from the quantum chaos. Let that sit for a moment. The difference between a photon and an electron, between light and matter, is now written into the background of the universe as a permanent choice of field value. Change that number and chemistry, stars. Even your brain's computation would be impossible. As the universe keeps expanding, it cools. Not 10 degrees, not 100 degrees, but from trillions of degrees down, step by step. Through energy scales we can only probe in particle colliders. Between about 10 and 6 seconds and a millisecond, quarks find each other and lock into triplets. Protons, neutrons, tiny composite machines built from confined quarks, like cooled slag in a blast furnace, suddenly snapping into solid metal. Every time a quark meets an antiquark, they annihilate into pure energy. The result should have been a perfect cancelling out, a clean ledger. But there is a gap. For every billion pairs that vanish, there is one extra quark, one extra lepton left over. We do not yet know why the universe cheated that way, only that it did, and that minuscule asymmetry is everything you have ever seen. By about 1 second, neutrinos decouple and stream off. The weak interactions freeze out, and the universe becomes a hot, dense plasma of photons, electrons, positrons, protons, and neutrons. No atoms, no light escaping. Just a glowing fog, smooth to 1 part in 100,000. If you are new here, this is the moment to pour yourself something warm and ask, how do you get from a nearly featureless fireball to stars, planets, and conscious observers? We will get to that, but the route from uniform plasma to structured reality hides one more surprise about how the cosmos remembers its own quantum fluctuations. Forged in the first minutes, primordial nucleosynthesis. The universe answered that question with fire. From about 1 second to a few minutes after the beginning, everything you will ever touch was inside a cosmic pressure cooker, not a metaphorical one. A literal, expanding nuclear reactor the size of the observable universe. In that brief window, a process called Big Bang nucleosynthesis switched on. Protons and neutrons colliding, fusing, and falling apart in a frenzy of quantum dice rolls that would decide the chemical menu for the rest of cosmic history. Here is the thing. The timing was brutal. At around 1 second, the temperature was so high that even if two particles fused, they were ripped apart almost instantly. At a few minutes, the universe had expanded and cooled so much that collisions became too rare for fusion to continue. Between those two limits was a narrow corridor where nuclear reactions could run, but not be immediately undone. Not millions of years, minutes. The main result of that brief computation was disappointment if you were hoping for complexity. About 3/4 of the mass stayed as hydrogen nuclei, lone protons. Roughly 1/4 froze in as helium-4, the same helium you put in party balloons. On top of that, just a dusting of deuterium, helium-3, and lithium-7. That is it. No carbon, no oxygen, no iron. The periodic table, in a sense it was, almost entirely blank. The bottleneck was deuterium, a proton plus a neutron. You needed deuterium as the first rung on the ladder toward helium. But the early universe was so hot that any deuterium nucleus was like an ice cube in a furnace. It formed, and the next photon that hit it blew it apart. Only when the temperature dropped below a very specific threshold could deuterium survive long enough to pile up. Let that sit for a moment. The entire later story of stars and life depended on the universe cooling through a tiny temperature window at just the right cosmic age. Too hot for too long, and almost no helium would form. Too cool too quickly, and reactions would freeze out before enough deuterium ever appeared. Change the balance of protons to neutrons by a few percent, tweak the expansion rate, and you get a universe with radically different chemistry, maybe one where long-lived stars never ignite. The gap between just hydrogen and a sky full of suns is only a small shift in early universe conditions. And the strangest part is not that we can write down the equations. The strangest part is that we can check them. When astronomers measure helium and deuterium in distant, pristine gas clouds, places that have never been through a star, they find the same fractions predicted from those first minutes to several decimal places. A machine made of telescopes and detectors is peering back in time and confirming that this nuclear recipe really happened, which means almost everything you care about did not. The carbon in your cells, the oxygen in your lungs, the iron in your blood, none of that was forged here. The early universe gave you a hydrogen-helium canvas and then walked away. The rest would require a new kind of engine, something far more violent than this gentle 3-minute burn. Stars had to be invented. And when they finally switch on, the difference they make to reality is so extreme that the universe starts writing a completely new chapter. The long dark, waiting for the first stars. So the universe has its hydrogen-helium canvas. The first atoms are in place, and then nothing happens. Not for a long time. Space keeps expanding, cooling, relaxing, but to your eyes it would look like the most boring movie ever filmed. No stars, no galaxies, no planets, just a vast, almost perfectly smooth fog of neutral hydrogen and helium, stretching in every direction, transparent, silent, unlit. Here is the thing. Transparent does not mean bright. The cosmic microwave background is still humming, but it has redshifted into microwaves, far beyond what any biological eye could see. The glowing plasma has recombined into neutral atoms, which no longer scatter light the way a fog or a cloud would. So the universe is, in a sense it was, crystal clear and utterly dark at the same time. On human scales, That feels impossible. On cosmic scales, it is just the next line in the script. The only structure in this darkness is written in tiny ripples of density, quantum fingerprints from inflation now frozen into the gas. Some regions are denser than average by a few parts in 100,000. Some are emptier. That is the entire difference. That tiny gap is the seed of everything. Gravity notices. Gravity always notices. Over tens of millions of years, it ever so slightly amplifies those overdensities, tugging more matter into the denser spots, letting the emptier regions drain. It is like watching sand very slowly slide into invisible dimples on a perfectly flat beach, except the beach is the universe, and the sliding is happening at the speed of expanding space-time. If you put this on a 24-hour cosmic clock, the Big Bang and recombination are happening in the first minutes. This long dark age, it stretches for hours, hour after hour of nothing to see, while every piece of history you recognize, Earth forming, dinosaurs, the internet you are using right now, will all flash by in the last seconds before midnight. Let that sit for a moment, and the strangest part is how patient the physics is. There is no dramatic explosion, no cinematic montage, just the invisible work of gravity running a vast, distributed computation on this neutral gas. No central machine, no control room, just the equations of general relativity and fluid dynamics quietly solving themselves. The result will be every galaxy cluster, every black hole, every planet that ever wonders why reality is the way it is. From recombination to around 100 or 200 million years after the beginning, the universe is a waiting room. The temperature falls. The first halos of dark matter and gas grow. The pressure in their centers climbs. Hydrogen begins to compress toward a critical threshold. And then, somewhere in that darkness, in one of those slightly denser regions, the numbers finally line up. A core passes the point of no return. Nuclear fusion ignites. For the first time, light does not just travel through the universe, it shines from within it. What those first stars do next will rewrite the entire story. First light, the birth of stars and galaxies. Those first sparks are not gentle, they are monsters. Astronomers call them population 3 stars, but that name is almost misleading. It sounds like a software update. In reality, these are the first true engines of light the universe ever builds, made almost entirely of hydrogen and helium, with almost nothing else in the mix. No carbon, no iron, no planets, just raw fuel poured into a gravitational furnace. Here is the thing, without heavier elements to help radiate heat away, the collapsing gas clouds don't stop at sun-like sizes. They overshoot. Many of these first stars may have been 100 times the mass of the Sun. Some models push them to 300. Let that sit for a moment. A single star holding more mass than an entire open cluster in our modern sky, burning so violently that its life is measured not in billions of years, but in a few million. How do you even build something that extreme? You start with a universe that is almost perfectly smooth, but not quite. Dark matter, invisible yet dominant, pools into halos, like a hidden scaffolding. Ordinary gas falls into those wells. As it collapses, quantum and classical physics fight a quiet war over pressure, cooling, and fragmentation. Pockets of gas break apart, each fragment spiraling inward until gravity wins and fusion ignites. The result is a brief, blinding blue giant, then another, then thousands. And the strangest part is not how bright they are. The strangest part is how fast they die. In just a few million years, many of these giants reach the end of their computation, run out of fuel, and tear themselves apart in supernova explosions that would make our sun's eventual death look like a sparkler. Some collapse into black holes, seeding the young universe with gravitational traps that will later anchor entire galaxies. Those dark matter halos don't stay isolated. They merge, again and again. Small clumps collide. Stars slingshot past one another. Gas is shocked, compressed, stripped, and pulled back in. Hierarchical assembly turns tiny star clusters into the first protogalaxies. Not yet the graceful spirals and smooth ellipticals you know now, but warped, lopsided machines of chaos, where every orbit is an improvisation, and every close pass can trigger another wave of starbirth. If you are new here, this is the moment where the universe starts to look busy. These first stars do something even more radical than forging heavy elements. Their ultraviolet light is so fierce that it rips electrons off neutral hydrogen atoms in the surrounding gas. Remember how, after recombination, the cosmos filled with neutral hydrogen and went dark. Rionization is the undoing of that calm. Slowly, bubble by bubble, the fog lifts. The universe becomes transparent again, not just to microwaves, but to a broad spectrum of light. Now pause and compare. You walk outside on a clear night and see a serene, slow sky, stars that live for billions of years, constellations that barely change over human history. In the first billion years, that serenity would have been an illusion. Massive stars flared into existence and detonated again in what, on cosmic timescales, was almost real time. Regions that were dark 1 million years could be blazing the next. In a sense, it was the universe's adolescence, loud, unstable, and wildly productive. And as those explosions enrich space with new elements, they quietly set up the next surprise in our story, the moment when light, gravity, and chemistry start conspiring to build worlds. Black holes, the dark engines at the heart of galaxies. Those newborn galaxies didn't stay innocent for long. Deep in their crowded star clusters, something even stranger than supernova fireworks was taking shape. The first black holes, the dark engines that would quietly take over the story of structure in the universe. Here is the thing. When the most massive early stars died, they didn't leave behind gentle embers. Their cores collapsed under their own gravity so completely that not even light could escape. The result was a gravitational machine with a one-way surface, an event horizon, and a singularity where our classical physics throws up its hands. Some of those black holes stayed small, but some merged over and over, while gas rained in around them like fuel. Let that sit for a moment. Out of the chaos of the universe's adolescence, you get these invisible wells that only grow by eating everything that wanders too close. As galaxies assembled, many of those wells sank toward the center, dragged in by friction with surrounding stars and dark matter. Over hundreds of millions of years, they fattened into monsters millions, even billions, of times the mass of the Sun, the supermassive black holes now lurking in almost every galactic core, including ours. And the strangest part is not that they are there. The strangest part is how loud they can be. When gas spirals into a central black hole, it doesn't just fall. It slams into itself, heats up, and forms a blazing accretion disk. In its hungriest phases, that disk can outshine the entire galaxy around it. We call these feeding frenzies active galactic nuclei and, at their most extreme, quasars. They launch jets of particles that can pierce intergalactic space for hundreds of thousands of light years. Stop and think about the difference that makes. Those jets and that radiation are not cosmetic. They punch holes in surrounding gas, shut down star formation in some regions, and compress it in others. A single quasar can decide whether a galaxy becomes a quiet spiral with long-lived stars and stable planetary systems, or a red, dead elliptical where the lights go out early. If you are new here to this kind of cosmic engineering, it sounds impossible that something you cannot see directly is doing urban planning on galactic scales. Yet observations keep pointing to the same conclusion. There is a tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy's bulge of stars. Tiny dark heart, small galaxy. Giant dark heart, giant galaxy. In a sense, it was a negotiation written in gravity and energy feedback. Grow the galaxy, grow the black hole, grow the black hole, regulate the galaxy. Which means black holes are not just endpoints, They are engines of structure, redistributing matter, heat, and heavy elements, quietly influencing where calm, long-lived, life-friendly environments can exist. And we will get to the quantum mysteries hiding at their horizons later. For now, keep one more image in mind. When the bright era of stars ends and galaxies fall silent, these same black holes will still be there, waiting. In the far future, when almost everything else fades, they will be the last significant actors left on the cosmic stage. Heavy metal, how stars built the ingredients for life. Black holes may write the final chapter, but the middle of this story belongs to stars. Think of each star as a machine running a continuous nuclear experiment. In its core, gravity has crushed matter so hard that hydrogen nuclei fuse into helium, releasing light and heat as the receipt for the energy transaction. That quiet, relentless fusion is what holds back collapse, what turns a cold quantum vacuum into a warm, habitable sky. Here is the thing. Stars do not stop at helium. In heavier stars, the core becomes a layered factory, almost like an onion made of fire. Deep inside, helium fuses into carbon and oxygen. Above that, new shells ignite, carbon into neon and magnesium, oxygen into silicon, silicon into iron. Each layer is a different reaction, a different chapter of stellar computation, all running in parallel until the machine hits a hard limit. That limit is iron. Fusing elements up to iron releases energy. Try to fuse iron into something heavier, and the math flips sign. You have to put energy in instead of getting energy out. For a star whose entire existence depends on fusion, paying its own bills, that is a fatal accounting error. When enough iron piles up in the core, the balance sheet breaks. Gravity wins. The result is one of the most violent transitions in the universe, a core collapse supernova. In a fraction of a second, the core implodes, rebounds, and hurls outer layers into space with more power than billions of ordinary suns. In those brief, impossible conditions, with densities and temperatures that make normal matter look fragile, nuclei are slammed together into elements beyond iron: gold, uranium, iodine, and the rest of the heavy periodic table. And the strangest part is, supernovae are not the only overachievers. When two neutron stars spiral together and collide, their shredded cores become another forge for these ultra-heavy elements, ejecting jets of radioactive debris that cool into the metals we mine and the atoms we quietly carry around in our bodies. If you are new here, let that sit for a moment. The carbon in your cells was built in the helium-burning heart of a long-dead star. The oxygen you are breathing right now was cooked in hotter shells above it. The calcium in your bones is star ash. The iron in your blood is the direct memory of a collapse that ended in a supernova. Every breath you take is recycled stellar atmosphere. Every sip of water is hydrogen from the Big Bang married to oxygen from stellar furnaces, the liquefied ashes of suns that failed gracefully enough to share their remains. In a sense, it was a kind of cosmic composting program, turning dead stars into planets, oceans, and eventually nervous systems that could ask where they came from. By around 9 billion years after the beginning, those metals have spread through spiral galaxies, seeding cold clouds with just enough heavy elements to build rock, chemistry, and complexity. In one quiet arm of one such galaxy, a new star will ignite with exactly the right mix. Around it, disks of dust and ice will start to clump. World-sized experiments in reality will form. One of them will be ours. What happens when that newborn system discovers the universe that built it? A quiet star in a suburban galaxy, the birth of the sun. To answer that, we have to zoom in, way in, from the grand computation of the universe down to one quiet experiment in a suburban spiral arm of the Milky Way, the birth of a very ordinary star that will make an impossible difference to you and me. Roll the clock back 4.6 billion years. No sun, no Earth, just a cold, dark molecular cloud drifting around the galaxy, a vast fog of hydrogen, helium, and dust grains so thin that a cubic meter might hold a few hundred atoms, silent until something hits it. A nearby massive star dies, detonating as a supernova, and its shockwave slams into that cloud like a cosmic hammer. Here is the thing. Gravity loves an excuse. That passing blast compresses the gas just enough that its own weight takes over. Regions inside the cloud begin to collapse, pulling in more material, heating as they fall. At first, it is messy and lumpy and chaotic. But there is one rule the universe will not bend: conservation of angular momentum. As the cloud core shrinks, any tiny initial spin gets amplified, faster, tighter. The collapsing region flattens into a spinning disk, a cosmic record around a growing central knot. Most of the mass spirals inward, crushed until nuclear fusion finally ignites. In a sense, it was an explosion in reverse, gravity doing the work up front so the fire can burn for billions of years. That newborn furnace is our sun. Not 100% of the material makes it in. The leftovers, dust, ice, pebbles, collide and stick in that disk, first into grains, then boulders, then mountain-sized planetesimals. Through endless impacts, some of those become planets, moons, comets, and asteroids. You are looking at a debris field that learned orbital mechanics. And the strangest part is not that we can simulate pieces of this with classical computation. The strangest part is what we find when we crack open the debris. Meteorites carry radioactive isotopes like aluminum-26 and heavy elements like gold, uranium, and iodine. They are fingerprints. They tell us our cloud was seeded by older stars that lived, fused, exploded, and enriched the galaxy long before the sun existed. Let that sit for a moment. Your bones, your blood, your phone, all borrowed from at least a second or third generation star graveyard. Compared to those violent ancestors, the sun is chill. A middleweight G-type star, not too big, not too small, with a main sequence lifetime of about 10 billion years. It burns steadily, not in wild flares that sterilize worlds, but in a long, remarkably stable phase where light and heat barely drift over geological time. In cosmic terms, this is an unusually calm neighborhood, a safe lab bench for chemistry to run. Pattern interrupt. Think about the warmth of sunlight on your skin the last time you stepped outside. That gentle heat, that pleasant glow, is the surface whisper of a nuclear machine 150 million kilometers away, where hydrogen nuclei are smashing together at quantum scales to release energy that took tens of thousands of years to random walk out of the core and just 8 minutes to cross the vacuum to you. That beam began in a chain of stellar deaths spanning billions of years. If you are new here, pour yourself something warm and hold on to that feeling of sunlight, because in the next section, we are going to follow one tiny planet in that disk as it cools, cracks, and somehow wakes up enough to ask what reality is. From molten rock to blue marble, Earth takes shape. So here is the thing, that gentle sunlight on your skin was forged in violence. To get a planet calm enough to host you, the universe first had to build a shooting gallery. 4.5 billion years ago, the newborn sun sat inside a whirling disk of rock, metal, and ice. Not planets, not worlds, just billions of shards, from dust grains to mountain-sized boulders, all orbiting, colliding, shattering, and merging. Imagine a construction site where the cranes are moving at tens of kilometers per second, and nobody filed a safety plan. In that chaos, gravity was running a long, slow computation. Clumps attracted more clumps. Pebbles became planetesimals. Planetesimals became protoplanets. Each impact converted orbital energy into heat, until one of those growing bodies, our proto-Earth, was less a world and more a glowing sphere of magma. No continents, no oceans, just a global lava ocean, constantly resurfaced by incoming projectiles. And then, something even more extreme. A Mars-sized object, often called Theia, slammed into that molten Earth. Not a glancing tap, a world-ending, world-making collision. The result was catastrophic. Rock vaporized, plume of debris blasted into orbit, the entire surface reset. But in a sense, it was an act of cosmic engineering. That ring of incandescent rubble circled the wrecked planet and, over tens of millions of years, clumped into a single unusually large moon. Stop and think about the difference that makes. Most rocky planets, as far as we can tell, do not get a moon this big relative to their size. Our moon grips Earth with its gravity, slowing our spin, stabilizing our axial tilt. Without that, Earth's orientation could wander chaotically, flipping climates like a broken thermostat. With it, we get seasons that change, but not too much. A long-term, semi-predictable rhythm. Let that sit for a moment. Meanwhile, Earth's interior kept behaving like a furious machine. Radioactive elements decayed, stirring the mantle, driving volcanic eruptions that belched gases into the sky. Early on, the atmosphere was a choking mix of carbon dioxide, water vapor, sulfur compounds, maybe a whisper of nitrogen. No oxygen, no blue, just a pressure cooker wrapped around a cooling ball of rock. Water arrived both from within and from above. As the magma oceans solidified, dissolved water bubbled out through volcanoes. Icy comets and primitive asteroids added more, delivering cargoes of H2O and organics over hundreds of millions of years. At first, the surface was too hot. Liquid water flashed to steam. But as impacts slowed and the planet radiated its heat away, a threshold was crossed. For the first time, raindrops could fall and stay. Oceans pooled in the low places. Thick clouds reflected sunlight. Carbon dioxide dissolved into seawater and locked into rock. The hellscape dimmed down into something merely hazardous. Not friendly, just less lethal. Here is the part that often gets flattened into a single phrase: habitable zone. On paper, Earth sits in the Goldilocks band where, at our distance from the sun, liquid water can exist on the surface. That sounds clean. It sounds like a simple orbital address. But habitability is not a line on a diagram. It is a balancing act performed by an entire planet. You need a magnetic field, generated by a still molten convecting core, to shield the atmosphere from the solar wind. You need plate tectonics to recycle carbon between rocks, oceans and air, acting as a planetary thermostat over hundreds of millions of years. You need the right chemical composition, enough heavy elements for complex minerals, but not so much radioactive heat that the crust never stabilizes. You need long-term climate regulation that can ride out stellar tantrums and orbital wobbles without freezing everything solid or boiling everything off. Change any of those parameters by a modest amount, and you do not get a blue marble. You get a Venus with a runaway greenhouse and a surface hot enough to melt lead. Or a Mars with a thin, failed atmosphere and oceans that never lasted. On cosmic averages, Earth is not typical. It is weirdly tuned. And the strangest part is, even after all that improbable tuning, for hundreds of millions of years, Earth was still just chemistry. Minerals, metals, oceans, storms. No minds, no microbes, just reactions. Then, somewhere around 700 million years after Earth formed, in those dark oceans under an alien sky, something happened that no classical geologist could have predicted. Certain molecules began to copy themselves. Information started to matter. Chemistry began to cross the line into biology. In the next section, we are going to zoom all the way down into that microscopic frontier and watch the universe teach a puddle of molecules how to evolve. Life's first spark, from chemistry to cells. So let's walk into that puddle the universe just invented and see what it's actually doing. Early Earth was not a gentle blue marble. It was a chemical engine turned up to 11. Superheated hydrothermal vents roared along newborn ocean ridges, blasting mineral-rich water into the dark. Tidal pools along volcanic coasts filled and evaporated, over and over, concentrating whatever the cosmos had thrown in. Even ice-covered oceans, with frozen lids and liquid water below, may have acted like slow-motion laboratories. Into all of that, the universe dumped ingredients. Some brewed locally in lightning-lit atmospheres and hot rock cracks. Some arrived from space, riding in comets and carbon-rich meteorites that slammed into the surface and then quietly dissolved, seeding the oceans with organic molecules. Not life, but a vocabulary of carbon chains, simple sugars, primitive lipids, and, crucially, the building blocks of RNA and DNA. Here is the thing. None of that is alive. It's just chemistry, churning. But somewhere in those vents, or those pools, or under that ice, a new pattern appeared. Molecules that did something outrageously illegal by classical geology standards. They copied information about themselves. One leading idea is called the RNA world. Imagine short strands of RNA that can both store information and help reactions happen. A molecule that is, in a sense, its own instruction manual and its own tiny machine shop. Some versions fold into shapes that encourage copies to form. Copies that are not perfect. Copies that compete. You can feel evolution warming up in the background. Let that sit for a moment. We have left the world of passive rocks and fallen into a regime where matter is running a kind of computation on itself. The question is no longer, what chemicals are here? But, what information do they encode, and how good are they at making more of it? Life is what happens when that question starts to dominate reality. When clumps of atoms trap free energy from the environment and use it to maintain patterns that would otherwise be erased by entropy. A cell is not just complex material, it is a machine that preserves a very specific arrangement of atoms by constantly pushing back against the default slide into disorder. And the strangest part is how neatly this plugs into the cosmic story you and I have been tracing. Stars forged heavy elements, supernovas scattered them, planets condensed. Now, on at least one of those worlds, the universe has found a new way to organize matter and energy. Self-replicating, information-bearing islands that remember how they were built. If you are new here, this is the moment where the universe stops being only a place and starts becoming a process that learns. But for a very long time, that learning is microscopic. For billions of years, Earth is a planet of films and films of single cells, quietly mutating, competing, collaborating. No forests, no animals, no brains. So what snapped? What flipped this planet from a bacterial ocean into a world of towering trees, giant reptiles, and eventually a species that can build particle colliders and wonder why anything exists at all? We will get to that. Complexity wakes up from single cells to conscious brains. So here is the thing, nothing snapped in a single moment. The rise from slime to mines was a slow, brutal computation running on a wet rock for billions of years. If the universe is one enormous machine for exploring what is possible, then life is the subroutine that refused to quit. First big move? Photosynthesis. Some early microbes learned to grab sunlight and use quantum chemistry to strip electrons from water, spitting out oxygen as waste. Harmless at first, then catastrophic. Over hundreds of millions of years, that oxygen rusted the planet and poisoned most of the old anaerobic world. Mass extinction as a side effect of a new energy technology. Let that sit for a moment. But oxygen also unlocked a new game. With it, cells could run far more efficient metabolism, like upgrading from a hand crank to a fusion reactor. That set the stage for one of the strangest mergers in the history of reality. Endosymbiosis. A big cell swallowed a smaller, energy-dense bacterium and didn't digest it. In a sense, it was an ancient corporate takeover that worked. The captive power plant became the mitochondrion. The host became a eukaryotic cell. Those eukaryotes could get larger, more complex, with internal compartments and longer genomes. Still single cells, but now the hardware was there for something new. Multicellularity appears, probably many times, as cells stick together, specialize, and agree, through chemistry. Not to all reproduce at once. Some become muscle, some become skin, some, eventually, become neurons. Once you have multicellularity, you can build networks, nerve nets in jellyfish, simple cords in worms, then centralized bundles we call brains. Senses feed them data. Brains compress that data into models of the environment. Suddenly, this planet is running predictive simulations inside skulls. An animal doesn't just react. It can plan, hesitate, deceive. That is a very different kind of computation than a microbe drifting towards sugar. And the strangest part is the timing. Life shows up on Earth quickly, within a few 100 million years, but complex animals with real nervous systems, they wait more than 3 billion years, until the Cambrian explosion about 540 million years ago, when body plans go wild, shells, eyes, claws, spines. If you are new here, this is the part where we zoom out, map all of cosmic history onto a single day. The universe wakes up at midnight with the Big Bang. Stars and galaxies form by early morning. Earth appears in the afternoon. Single cells dominate through the long, quiet evening. Complex animals show up in the last few minutes before the next midnight. Humans arrive in the final fraction of a second. On that clock, intelligence is not early. It is a photo finish. Pattern interrupt. Picture a single neuron firing in your brain right now. An electrical spike races down a branching tree of membrane. Ions shuffle. Information moves. Freeze that image. Now jump to a cluster of galaxies, hundreds of millions of light years across, threads of dark matter and gas exchanging energy, gravity shuttling information about mass and motion across cosmic distances. Different scales, same game. Matter arranging itself to carry correlations forward in time. That is the gap we crossed on this planet, from blind chemistry to conscious modeling. And it took almost the entire age of the universe so far. Does that mean minds like ours are rare, or just slow to boot on any given world? We will get to that. Self-aware stardust, humanity enters the story. So here is the thing. After 13.8 billion years of blind quantum and classical computation, of particles and fields just following equations, the universe does something outrageous. It grows a creature that can look back and say, wait, what was all that? That creature is you. Homo sapiens show up around 300,000 years ago. Not 3 billion, not 300 million, 300,000. On a 4.5 billion year Earth, that is the last pixel in the last frame of the movie. On the full 13.8 billion year cosmic timeline, we appear so close to the end credits that if you blink, you miss us. Let that sit for a moment. For most of that time, our ancestors carry stone tools and fire, and that is about it. The same planet that built continents and oceans over hundreds of millions of years watches us go from chipped rocks to agriculture in maybe 10,000, then to cities and writing in a few thousand more, then to telescopes, antibiotics, nuclear reactors, and smartphones in a few centuries. And the strangest part is not the speed. The strangest part is what that acceleration really means. In that tiny sliver of time, a primate brain that evolved to throw rocks and gossip in small groups starts reconstructing the first microseconds after the Big Bang. You and I sit here while machines in underground tunnels smash particles together to recreate conditions from when the universe was less than a second old. Space telescopes catch photons that have been flying for billions of years, and we turn those signals into a baby picture of the cosmos. In a sense, it was inevitable once chemistry learned to think. We become a way for the universe to model itself. Raw photons hit your retina or a CCD sensor and end up as equations about inflation, dark matter, and the heat death trillions of years from now. A brain, this wet, fragile machine of ions and membranes, runs simulations of galaxies colliding and black holes evaporating. Where exactly is that computation happening? We will get to that. But there is a twist. Our technological civilization is not just watching, it is pushing back. In a few centuries, we have altered Earth's atmosphere, climate, oceans, and biosphere on timescales that used to belong only to asteroid impacts and supervolcanoes. The long-term habitability of this planet is now entangled with choices made by a species that did not exist for 99.9996% of Earth's history. So we find ourselves in a paradox. Self-aware stardust with the power to derail or extend the only cradle we have. What do we do with that? Pour yourself something warm and really think about it, because this is the pivot point of the story. Up to now, we have raced from the first fraction of a second to the brief moment when you appear. In the next part, we flip the arrow of time forward again and follow what happens from here, through our era, beyond the death of the sun, and all the way to the end of the universe. Part 2. The Age of Stars. Our bright but brief moment. So here is the thing. From this pivot point, the story changes direction. Up to now, we have been racing toward you. From now on, we are watching the light slowly drain out of the universe. Welcome to Part 2, the Age of Light. This is the era when stars still burn, when galaxies still collide and weave new suns out of cold gas, when the night sky is not an empty black ledger, but a crowded field of fire. This is the stelliferous era, the star-making chapter of cosmic history, and you and I are right in the middle of it, not metaphorically, literally. In cosmic terms, we live in the bright noon of starlight. The first stars ignited a few 100 million years after the Big Bang, when the universe was a fog of hydrogen and helium just cool enough to let gravity get ambitious. Since then, for billions of years, the great stellar machine has been running. Clouds collapsing, fusions switching on, heavy elements cooking in cores and detonations, planets coalescing out of the ashes. Everything you can see with your naked eye belongs to this one shimmering phase. And the strangest part is, it is temporary. It feels permanent because every memory you have, every classical intuition your brain trusts, was shaped inside this bright window. But the stelliferous era is only a chapter, not the book. It will last on the order of trillions of years, stretched absurdly far beyond any human scale. Yet in a sense, it was already past its climax before Earth even formed. Let that sit for a moment. When you look up now, it is easy to think the universe is still ramping up. New stars are being born in Orion, in the Carina Nebula, in the dusty arms of the Milky Way. But if you rewind the tape a few billion years, the difference is brutal. Back then, galaxies were smaller, denser, richer in raw gas. Star formation was 10, 20 times higher than it is today. The cosmos was more crowded, more violent, more luminous. We tend to imagine we arrived for the fireworks. In reality, we showed up just after the grand finale, while the machine is already winding down. In other words, we came to the party late. Most of the champagne has been opened, the brightest rockets have already gone off, and the host has quietly turned the music down a notch. Star formation has been declining for billions of years and will keep dropping as galaxies run out of fuel and dark energy pushes them farther apart. The lights are not off yet, but someone is definitely reaching for the dimmer. If you are new here, this is the part where the timeline stops being comforting. Because next, we're going to narrow the camera from the whole universe down to one yellow star and one spiral galaxy. We will get to the sun's remaining fuel, the Milky Way's long-scheduled collision with Andromeda, and how both fit into the slow extinguishing of starlight everywhere. Pour yourself something warm. From here on, we are walking forward into the dark. Our star's clock, the sun's life and death. So let's narrow the camera all the way down. Out of all the stars in the Milky Way, we are orbiting one very ordinary yellow machine that quietly controls everything about your day, your climate, your future. And the strangest part is, its clock is already halfway run. The sun is about 4.6 billion years old. Not 10 million, not 100 million, billions. Stellar evolution models, calibrated on star clusters and nuclear physics, tell us it has around 5 billion years of main sequence life left, burning hydrogen in its core in a remarkably stable nuclear computation. In stellar terms, it is in comfortable middle age, not a newborn, not yet an elder. Here is the thing. Stable does not mean unchanging. As the sun fuses hydrogen into helium, the core slowly contracts, heats up, and the luminosity creeps higher. The result is subtle now, but over hundreds of millions of years, that small percentage increase compounds. You experience it as a perfectly ordinary blue sky. Planetary climate models experience it as a ticking time bomb. Run those models forward, and something brutal appears. In about 1 to 2 billion years, long before the sun turns into a red giant, Earth is expected to tip into a runaway greenhouse. Oceans evaporate. Water vapor, a potent greenhouse gas, traps more heat, which evaporates more ocean. The feedback loop closes. This is not a gentle beach day warm-up. This is the atmosphere turning into a pressure cooker. Stop and think about that in classical human timescales. Civilizations rise and fall over thousands of years. Continents drift over tens of millions. But the biosphere's comfortable window, with liquid oceans and complex life, is maybe another billion. There is a hard upper limit baked into our local reality. If you are new here, that might sound like cosmological clickbait. It is not. Even if our descendants become a spacefaring civilization, even if we turn the inner solar system into a machine of habitats and mirrors and shields, the original Earth, the one with rain and forests and crows stealing your lunch, has an expiration date. Fast forward further. In about 5 billion years, hydrogen in the sun's core runs low. The core contracts, the outer layers expand, and the sun swells into a red giant. Its radius will grow tens to hundreds of times. Mercury is gone. Venus is gone. Earth, that one lives right on the edge. Some simulations say the orbit expands just enough. Others say the swollen sun's atmosphere drags our planet inward and swallows it. Either way, the surface is long dead. At the end of that phase, the sun sheds its outer layers into a glowing planetary nebula, a brief, eerie shell of ionized gas. What remains is a white dwarf, a hot, Earth-sized core. No more fusion, just residual heat radiating into the dark for trillions of years. In a sense, it was the sun's final data dump, the last result of 10 billion years of nuclear arithmetic. Let that sit for a moment. Every sunrise you have ever seen is one tick of a finite clock. And yet, even when our star is a cooling ember, the Milky Way will still be busy. Other stars will still be forming, colliding, being torn apart by black holes. Our galaxy is already on a slow-motion collision course with Andromeda. So what happens when not just one star, but entire galaxies begin to age, merge, and run out of fuel? We will get to that. Galactic ballet, collisions, mergers, and the fate of the Milky Way. So here is the thing. Galaxies do not live quiet, solitary lives. They grow the way cities do, by merging, absorbing, colliding, turning small neighborhoods of stars into sprawling, tangled metropolises of light. From the very beginning, tiny proto-galaxies orbited one another, spiraling in, their dark matter halos overlapping first, their stars mostly missing each other, but their gas smashing together like slow-motion traffic. Stop and think about that in classical terms. In a head-on collision between two galaxies, almost every star avoids every other star. The distances are that absurd. It would be like firing two swarms of bees through each other and watching every bee pass cleanly between the wings of the others. And yet, the thin, cold gas between those stars does collide, compressing, heating, collapsing into new stellar nurseries. The result is a starburst, a brief, furious episode of star formation that can turn a once calm spiral into a blazing, infrared-bright machine. Our own galaxy is not an exception to this story. The Milky Way has already eaten smaller companions. You can still see the shredded streams of their stars wrapping around us like ghostly rivers. And now, another partner is inbound. Andromeda, a spiral roughly our size, about 2.5 million light-years away, closing the gap at roughly 100 kilometers per second. That sounds fast. It is. But on galactic timescales, this is a slow dance. In about 4 to 5 billion years, the two spirals will finally interpenetrate, their disks passing through each other again and again as gravity reshapes them into a single, bloated remnant. Astronomers have even given that future hybrid a name, Milkdromeda. In a sense, it was inevitable from the moment these halos first coalesced. And the strangest part is not the violence. The strangest part is how gentle it will feel locally. Your night sky would transform beyond recognition, but your backyard would probably remain intact. Individual stars and planetary systems are so far apart that direct collisions are extremely unlikely. Space is mostly vacuum, and vacuum is very good at social distancing. Pattern interrupt. Forget the timeline for a second and look up with me from a hypothetical future Earth, or from a colony world that survived the sun's red giant tantrum. At first, Andromeda is a faint smudge, a little bigger than the moon if you know where to look. Then, over millions of years, it swells, not 2 times bigger, not 10 times, but eventually spanning half the sky. 2 great whirlpools of light, Milky Way and Andromeda, overlapping, twisting, turning the night into a double galaxy panorama. Pour yourself something warm and let that sit for a moment. Above you, hundreds of billions of suns, interleaved like gears in some impossible cosmic machine. In the core of each galaxy, supermassive black holes spiral toward each other, feeding on infalling gas, flaring as quasars that outshine entire galaxies. Those same mergers that ignite new stars also funnel material inward, powering the brightest beacons in the universe. But there is a cost. Every burst of star formation locks gas into stars. Every quasar episode heats and blows gas out into intergalactic space. Over time, Milkdromeda will settle into a smooth, rounded elliptical or lenticular galaxy, redder, quieter, with most of its gas exhausted. Star birth will slow, then dwindle. So if the middle age of the universe is a galactic ballet, what happens after the music fades and the last great mergers end? We will get to that. The great dimming. When the universe runs out of fuel. When the music fades, something more unsettling happens than silence. The lights themselves start going out. Not all at once in some dramatic cosmic blackout, but through a slow, relentless dimming that turns the universe from a bright blue carnival into a tired red afterparty. Here is the thing. Star formation is not automatic. It is a fragile kind of computation that galaxies run on cold gas. You need vast clouds of hydrogen and helium cooled down enough that gravity can grab them, squeeze them, and ignite new suns. That is the fuel. That is the difference between a living galaxy and a graveyard. Over time, that fuel gets locked away. Every new generation of stars sequesters gas in their cores. Supernovae and black hole jets blast some of it completely out of galaxies, into intergalactic space where it is too diffuse to do much. The rest is stirred and heated by stellar winds, by mergers, by those violent quasar episodes we just talked about, until it is too hot and puffy to collapse. Hot gas resists gravity. Hot gas does not want to form stars. On human timescales, the Milky Way looks stable. On cosmic timescales, it is burning through its inheritance. Give the universe tens of billions of years, then hundreds of billions, and you watch a very clear trend. The star formation rate plummets. Not 10%, not 90%, but orders of magnitude. Galaxies like Milkdromeda will still be there, but their nurseries will be mostly empty cribs. And the strangest part is, the stars that do remain are not the glamorous ones. The big blue giants that light up nebulae and headline Hubble posters die fast. They are gone in a few million years. The real survivors are the low-mass red dwarfs, the tiny, cool, miserly machines of fusion that can sip their fuel for trillions of years. In a sense, it was always their universe. We just arrived during the brief fireworks show of the bright ones. As the centuries of galaxies tick over into trillions of years, the stellar population shifts. Fewer hot blue stars, more cool red embers. The cosmic background itself has long faded into radio. the whole scene takes on a deeper, rusted hue. If you are new here, this is the part where the universe feels like it is aging in real time. Run the clock forward to around 100 trillion years, and something decisive happens. Star formation, in any meaningful sense, stops. The cold gas is gone, ejected, or permanently heated. No new clouds collapse, no new suns ignite. From that point on, the story is simple and brutal. The existing stars just age, flare, and go out. Pour yourself something warm and let that sit for a moment. Once the last generation of stars is born, a countdown begins, not to the end of the universe, but to the end of starlight. When the final red dwarfs burn through their last atoms, and the last white dwarfs cool to black, what fills a universe where no new stars can ever turn on again? The last suns, red dwarfs, and the final fires. And here is the thing, that countdown is wildly unfair. Because the stars you and I grew up with in our imagination, the big blue giants, the golden suns, are not the main characters of this story. They are the fireworks. The real protagonists of the Age of Stars are tiny, dim, and so patient that our entire civilization flashes by like a quantum glitch in their day. Red dwarfs, the smallest, coolest, most common stars in the universe. Some are barely 8% the mass of the Sun, just above the threshold where gravity can ignite hydrogen fusion at all. Their surfaces glow at a few thousand degrees, not 10,000. To your eyes, they would look like sullen embers rather than blazing beacons, more like a machine on standby than one running at full power. That laziness is the secret. Because they are so light and cool, red dwarfs sip their fuel instead of guzzling it. They mix their interiors efficiently, pulling fresh hydrogen into the core, turning almost all of their mass into energy over time. The result is obscene. Lifetimes measured not in billions of years, but in trillions. Not 10 billion, not 100 billion, up to 10 trillion years and beyond, depending on the mass. Let that sit for a moment. Our universe is only about 13.8 billion years old. That means, in all of cosmic history so far, not a single red dwarf has had time to die of old age. Everyone that has ever formed is still out there, still burning, still contributing to a sky we will never see. In a sense, it was never about us at all. We live in the noisy prologue before the long, quiet middle chapters. Fast forward hundreds of billions of years. The hot blue giants are gone. Sun-like stars have swollen, shed their outer layers, and cooled into white dwarfs. If you were an observer, then, on some world that beat impossibly long odds, you would look up into a night ruled by red. Faint, ruddy points everywhere, no bright Orion, no Milky Way band, just a sparse lattice of low-wattage stars separated by ever-growing darkness. And yet, around many of those embers, there would still be a warm zone, a narrow shell where liquid water could exist for tens or hundreds of billions of years at a stretch. Long after Earth is a memory encoded only in drifting atoms, planets could circle these red dwarfs in slow, stable orbits, running their own experiments in chemistry, biology, and maybe consciousness. How many cycles of life and extinction fit into a trillion-year window? How many rises and falls of intelligence happen after our chapter closes? If you are new here, this is the part where the universe gets rude again, because even these patient stars do not get infinite time. Their hydrogen runs out. Their light reddens, then fades. One by one, the last suns wink off, leaving behind cooling husks and stellar corpses. When the final red dwarf flickers out, what is left to write the next page of reality? Part 3, the era of corpses, white dwarfs, neutron stars, and black holes. What is left is not silence, it is part 3, the age of remnants. The bright, adolescent universe you and I are used to is gone. In its place stretches a graveyard that still moves, still calculates, still writes reality with the cold precision of gravity. Let that sit for a moment. The cosmos does not end with the last star's last photon. It just promotes new main characters. Here is the thing, when a star dies, it rarely disappears. It leaves a core. For sun-like stars, that core is a white dwarf, the exposed Earth-sized ember of a once luminous machine. No fusion, no new light being minted, just leftover thermal energy leaking into the dark. A teaspoon of white dwarf matter would outweigh a skyscraper, yet the whole object glows like a hot coal, cooling over trillions of years until it becomes almost indistinguishable from the night around it. More massive stars slam past that outcome. Their cores are squeezed so hard that electrons and protons merge, and you get a neutron star, a city-sized sphere with more mass than the sun. Spin that, thread it with a magnetic field, and you have a pulsar, a lighthouse in a dark ocean, sweeping beams through space with millisecond precision. In a sense, it was the universe's way of discovering extreme engineering. Quantum degenerate matter, classical rotation, and magnetic fields all welded into one impossible object. Push the mass higher still, and even neutrons lose. Gravity wins outright. The result is a black hole, an object where escape velocity outruns light itself. Cross its event horizon and, as far as classical physics is concerned, you are gone from the visible story. But your mass, your information, still changes the gravitational script. Space curves, orbits shift, time itself stretches. As star formation winds down and then stops, the demographics of the universe quietly invert. Right now, galaxies are lit by main sequence stars, those steady hydrogen-burning engines. Given enough time, every one of those engines exhausts its fuel and steps off the main stage, leaving behind a white dwarf, a neutron star, or a black hole. Not 10 million years, not 10 billion years, but over intervals so long that human language collapses, the luminous population drains away, and the cemeteries take over. And the strangest part is, this graveyard is not static. Remnants orbit. They scatter off each other. They spiral together, merging in flashes of gravitational waves that ring across the cosmos. Whole galaxies of corpses still dance. The universe is darker, but the computation of motion, of encounter, of collision keeps running. Pour yourself something warm and imagine that. A sky where almost everything you see is dead, yet still shaping reality. Because one class of remnant, black holes, is about to become the dominant authors of the far future timeline. They will not just eat stars and each other. Through a slow, quantum process called Hawking radiation, they will, in the end, begin to eat themselves. How does a thing that lets nothing escape slowly evaporate into nothing at all? Frozen embers, the fate of white dwarfs and neutron stars. So while black holes are busy very slowly erasing themselves from reality, something quieter is happening in the background. The universe is filling up with frozen embers. Dead stars that did not quite make it to the event horizon end up in a different kind of prison. Take a white dwarf. Same mass as the sun, give or take, crushed into something about the size of Earth. Not a metaphor. You take a star, strip away its outer layers, and gravity squeezes the core until electrons are packed so tightly that quantum rules push back. That pressure, electron degeneracy, is the only thing holding the whole machine up against collapse. When a white dwarf is born, it is scorching, temperatures of hundreds of thousands of degrees. It glows blue-white, then yellow, then red. And then, over billions, then trillions of years, it just cools. No new fusion, no new fuel. The heat is a finite bank account, and the universe is charging interest in the form of relentless radiation into the dark. Here is the thing. As these remnants cool, the atoms inside them can lock into a crystal lattice. Carbon and oxygen, solidified under absurd pressure, arranging themselves into a single, star-sized gemstone. Not a poetic flourish, a literal crystal, a cosmic diamond the size of a planet, hanging in space and glowing faintly like a coal that refuses to go out. Let that sit for a moment. Now, quick pattern interrupt. Think about a diamond ring, tiny, polished, held up under a jewelry counter light while someone whispers about eternity. Now scale that up. Not carats, kilometers. An entire dead star, a crystallized jewel, drifting through a night so cold that even starlight has become a rare event. The romance is still there. The reality is just orders of magnitude more terrifying. White dwarfs are not the only embers. Some stars die harder, crush more. If the core is heavy enough, electrons get overwhelmed and protons and electrons are forced together. You end up with a neutron star, a sun's mass in a city-sized sphere supported by neutron degeneracy instead. The magnetic fields are insane. The rotation speeds are ridiculous. These things can spin hundreds of times per second and beam radiation like a lighthouse run by a quantum engineer with no regard for classical health and safety. When neutron stars merge, the result is violent and creative. They shake space-time itself, launching gravitational waves you and I can now detect on Earth. They forge gold, platinum, uranium, and hurl those heavy elements back into the galaxy, seeding future planets, future machines, future brains that will one day wonder where their jewelry and reactor fuel came from. And the strangest part is that this is still the busy, energetic phase. Fast forward, far beyond the death of the last normal star, and you enter a regime of almost pure cooling and waiting. Most white dwarfs will fade into black dwarfs, cold, dark, invisible. But there is a speculative twist hiding in the mathematics. In an unimaginably distant future, after timescales like 10 to the power of 1/100 years, some physicists have argued that quantum tunneling might allow fusion to restart in the hearts of the coldest remnants. Not because they are hot, but because over a long enough timeline, the impossible gets a vote. Nuclei that should never meet can suddenly find themselves close enough to fuse. If that happens, a black dwarf could, with no warning, ignite and explode as a supernova. A black dwarf supernova. A delayed firework going off in a universe that thought it was done with light. It is speculative, yes, but it closes a strange loop. The same quantum rules that once held the star up could, in the end, help tear it apart. Pour yourself something warm and imagine that scene. A universe so old that galaxies are memory, so cold that only dead embers remain. And then, out of nowhere, a single silent region erupts. For a brief moment, there is light again. Not enough to change the final result, not enough to close the gap to heat death, but enough to remind you that the story of stars is written in quantum probabilities, not guarantees. We will get to the era after even those embers and flashes are gone, when black holes have finished their long evaporation and only the thinnest haze of particles remains. Because beyond the age of stars and black holes lies something even more unsettling. A universe where time keeps going, but almost nothing happens. The slow dance of gravity, orbits decay, and systems fall apart. So the lights go out, the last star flickers, the last flare dies, and you might think the universe finally gets to rest. It doesn't. Gravity never sleeps. Even in a mostly dark universe, there is motion. Lonely white dwarfs, neutron stars, black holes, frozen planets, all still orbiting, still tugging on each other, still running a slow, relentless computation in space-time. No fusion, no fireworks, just the quiet arithmetic of mass and distance, adding and subtracting energy over unimaginable spans of time. Here is the thing. An orbit is not a promise. It is a negotiation. Every close pass between two objects is a tiny trade. One gains a bit of speed, the other loses a bit. Do that once and nothing interesting happens. Do it a trillion times and entire systems rewrite themselves. Picture the faded ruins of something like our solar system, a quadrillion years from now. The star is long gone, maybe a black dwarf or a black hole. The planets, moons, and leftover debris keep circling. Now add one more ingredient: encounters. A passing remnant swings by, steals a little energy from an outer planet, and suddenly that world is on a wider, wilder path. Another encounter nudges it again. Not 10 orbits, not 100 orbits, but billions of orbits later, that same planet can be flung completely free, launched into the dark as a rogue. Let that sit for a moment. A world with oceans, mountains, maybe even fossils in its rocks, exiled into interstellar space with no star at all. In a sense, it was always on probation. Gravity just took a while to deliver the verdict. Scale this up and the story gets stranger. Star clusters and galaxies themselves are not static snow globes. They live through what astronomers call two-body relaxation. Every time two stars pass near each other, they exchange a tiny amount of energy. Most encounters are boring, but the statistical result, over 10-15 years and beyond, is dramatic. A few lucky stars gain enough speed to escape, while others sink deeper into the gravitational well. This is evaporation, but for galaxies. Clusters slowly leak their members into intergalactic space, populating the void with solitary wanderers. At the same time, the losers in this endless energy lottery spiral inward, feeding central black holes. Over absurdly long timescales, most bound systems face a binary fate: dissolve into a thin spray of escapees, or collapse into one or a few dominant black holes. By around 1015 to 1020 years, the universe is ruled by these isolated remnants and black holes, with only a sparse halo of rogue planets and orphan stars drifting between them. The grand cosmic web that once linked galaxies has thinned into something more like a scattered archive of failed experiments. And the strangest part is that this is not the end of the story. Because as gravity finishes its slow dance and hands the universe over to black holes, another process begins to whisper at the edge of reality. One that does not rely on gravity at all, but on quantum rules etched into space-time itself. We will get to that. Black holes. Fade. Hawking radiation and the end of darkness. And here is the thing. Once gravity hands the universe over to black holes, it looks like the end of the story. Eternal prisons, one-way traps, information in, nothing out. But that is the classical picture. The quantum picture quietly disagrees. In the 1970s, Stephen Hawking asked a question almost no one else was asking. What happens right at the edge of a black hole if you refuse to turn quantum mechanics off? The result was outrageous. A perfect absorber, a perfectly black object, is not perfectly black. It glows. It has a temperature. It leaks. To see why, you have to zoom in on what we call empty space. In quantum field theory, the vacuum is not nothing. It is a restless machine, constantly flickering with pairs of virtual particles that pop into existence and annihilate again too fast to count. Near an event horizon, that quiet background computation runs into a brutal boundary condition. One particle can fall in while its partner escapes. From far away, it looks like the black hole itself has emitted a particle. The escaping partner carries away a tiny bit of energy. The infalling one has negative energy relative to the whole and effectively subtracts mass. Not metaphorically. The black hole shrinks. The universe has found a way to make the impossible prison temporary. Let that sit for a moment. An object so dense that not even light can escape is, in a sense, it was designed by gravity to be final. Yet the quantum rules etched into space-time quietly undermine that finality, bit by bit. There is a twist in the scaling. Big black holes are cold, small ones are hot. A black hole with the mass of the sun would radiate at a temperature around a few dozen nanokelvin, far colder than the microwave background that currently bathes the universe. It will not start shrinking in earnest until the cosmos itself cools below it. Once the background fades, the countdown begins. A typical stellar mass black hole needs something like 10⁻�67 years to evaporate. Supermassive black holes at galactic centers drag the process out to 10-100 years or more. Not 10 billion, not a trillion, but a 1 followed by 100 zeros. Compared to those timescales, the current age of the universe rounds to 0. As a black hole loses mass, it heats up. Hotter means brighter. The radiation ramps from gentle whispers of long wavelength photons to a furious hiss of high-energy particles. In the final moments, what was once the dark heart of a galaxy ends in a brief, violent flash, a burst of gamma rays and elementary particles that tears the last coherent structure out into the thin, cold medium. After that, there is no horizon, no singularity, no machine left at all, just particles, photons, and an ever-thinning sea of energy. And the strangest part is what comes next. When the last black hole evaporates, the universe enters an era with no stars, no black holes, almost no gradients of any kind. What does time even mean when nothing much happens anymore? Pour yourself something warm, because the next phase is where reality stretches the idea of future far beyond anything our intuitions were built for. We will get to that. Part 4. The heat death. When nothing happens forever. This is part 4. The age of silence. The lights are out, the drama is over, and the universe is still expanding. Time keeps rolling. Almost nothing else does. Here is the thing. Up to now, every chapter of our story has been driven by imbalance. Hot next to cold. Dense next to empty. Gravity pulling, radiation pushing, quantum fields flickering. Those differences are what let anything interesting happen. Stars burn because their cores are hotter than their surroundings. You are alive because there is a temperature gap between your body and the night air. No gradient, no game. Physicists give that idea a name: entropy. In everyday language, you hear it called disorder, but that makes it sound like a messy bedroom. In reality, entropy is a count. It measures how many microscopic arrangements, or microstates, could give you the same big picture situation, the macrostate. Let that sit for a moment. It is not about how it looks. It is about how many ways it could secretly be arranged. Imagine a gas in a sealed room. At first, you release it from a tiny canister. All the molecules are crammed into one corner, low entropy, because there are not many ways to keep them that localized. Wait a while, and the gas spreads out evenly. Now there are astronomically many ways to shuffle those molecules while the room still looks uniform to you. That uniform state is high entropy. The same thing happens when ice melts in water. The crisp structure of the crystal has relatively few microstates. Melt it, and the molecules can wander almost anywhere. Entropy climbs. Now scale that intuition up to the entire universe. Heat death is what you get when that spreading out process has run as far as it can. Energy is still conserved, but it has been smeared so evenly across space that there are no temperature differences left to exploit. No hot cores, no cold voids in any useful sense, just a thin, almost featureless bath. There is still energy, but no free energy. No engine you could build, no life form you could imagine could extract work from it. And the strangest part is that the universe does not end with some final explosion or grand collapse. There is no last bang, no last crunch. Instead, you get an eternal whimper, an ever-expanding, cold, dilute soup of low-energy photons and lonely elementary particles drifting through an inflating darkness. Stop and compare that to the early universe. Not 10 billion degrees, not a million, but fractions of a second after the beginning. Temperatures so high that atoms could not exist, only a blazing plasma. Back then, reality was a roaring machine of gradients. Hot versus hotter, dense versus denser, quantum fluctuations being blown up by inflation. Now jump cut to the heat death era. No stars forming, no galaxies colliding, no black holes feeding. Just a clock that still ticks, but measures nothing of interest. This is the age of silence. The equations keep evolving. The cosmic computation keeps running. But from the inside, for any hypothetical observer, there is nothing left to notice. If that sounds final, hold on. The universe has one more twist to offer about what nothing happening really means, and it goes even deeper than heat death. Lonely particles, life and information at the end of time. So here is the thing. Nothing happening is not the same as nothing possible. Even in the age of silence, theorists have tried to imagine clever ways that life, or at least computation, might cling to existence for absurdly long times. Picture a civilization that has already outlived its stars. No sunlight, no fusion, just black holes, drifting photons, and the thin, cold breath of an expanding universe. What do you do if you still want to think under those conditions? You start treating the entire cosmos like a dying battery and squeeze every last usable drop of free energy out of it. One idea is to mine black holes themselves. You hover near the event horizon, catching energy from Hawking radiation as the hole evaporates. In a sense, it was the ultimate recycling program. Mass in, information out, computation powered by the slow unspooling of gravity's darkest machines. Others imagine harvesting the decay products of protons, if protons decay at all, or building Dyson sphere-like collectors around the faintest white dwarfs and neutron stars. Not 10 billion watts, not 10 million, but a handful of particles here and there, stretched over trillions of years. Freeman Dyson pushed this further with his eternal intelligence hypothesis. The trick was not to find infinite energy, but to spend finite energy infinitely slowly. Think a mind that runs one thought this year, one thought in a million years, one thought in a trillion, stretching subjective experience out by spacing its computations further and further apart as the universe cools. Pour yourself something warm and let that sit for a moment. A consciousness that survives by almost never thinking. It was a beautiful hack. And the strangest part is, later physics probably ruins it. Once you include accelerating expansion from dark energy, the observable universe shrinks around any given observer into a kind of cosmic bubble. Finite matter, finite energy, finite total computation. Quantum fluctuations and horizon temperatures set hard floors. You cannot cool your machines below the de-Sitter background. You cannot communicate beyond your local patch. You cannot beat the math. As expansion stretches space, everything gets worse. Energy sources fade, signals redshift and die. The gap between islands of matter grows faster than light can bridge. Thermal noise from the residual horizon temperature starts to overwhelm the delicate differences that encode information in any classical or quantum memory. Try running a computer when every bit flip costs more energy than you can afford. And then there is the problem of the archive itself. If protons decay, the very particles making up your hard drives, brains, and black hole accretion disks will eventually dissolve. If black holes evaporate, they release their information in a scrambled drizzle of low-energy radiation. Over unimaginable timescales, the physical record of what happened here, of galaxies, of life, of you, gets washed out into nearly featureless heat. So in the mainstream picture, not only does life die, the memory of life dies. Heat death is not just the end of activity, it is the erasure of history. But hold that funeral thought, because there are other endings on the table, endings where the universe does not fade out. It slams off suddenly, everywhere at once. We will get to that. Alternative endings, the Big Rip, torn apart by dark energy. So imagine this. Instead of the universe coasting into a cold, empty retirement, the accelerator pedal gets jammed to the floor. Space does not just keep expanding, it goes feral. To see how that could happen, we have to talk about dark energy. Right now, about 70% of the cosmos is this invisible pressure baked into space-time, pushing galaxies apart faster and faster. In our best fit model, it behaves like a cosmological constant. Same density everywhere, same strength at all times, a quiet background term in the equations that just will not go away. But here is the thing. That is an assumption. A good one, supported by the data we have, but still an assumption. Dark energy could be more exotic, a dynamic quantum field whose pressure changes over time. Physicists describe its behavior with a single parameter, W, in the cosmic equation of state. If W equals -1, you get the tame cosmological constant. If W is greater than -1, expansion still accelerates, but gently. If W drops below -1 though, the story turns apocalyptic. Let that sit for a moment. A value slightly less than -1 means dark energy does something outrageous. Its density increases as the universe expands. Every new bit of space is born with even more of this repulsive energy than the last. The result is a runaway feedback loop where expansion feeds on itself. In that scenario, called the Big Rip, the expansion is not just fast, it becomes stronger than every binding force in reality. At first, you would barely notice. For billions of years, galaxy clusters slowly thin out as the growing push of space overcomes the gravity holding them together. Trillions of stars that once orbited in graceful superclusters get flung onto lonely, diverging paths. Then the clock speeds up. As the rip approaches, whole galaxies are pulled apart. The gravity that binds their stars loses the tug of war with the swelling vacuum between them. Later still, solar systems go. Planetary orbits unwind as the space in between stretches more violently than the sun's gravity can compensate for. Closer to the end, the timeline gets brutally tight. In the last minutes, planets themselves are shredded as molecular bonds fail. In the last fractions of a second, atoms are torn open, electrons peeled away, then protons and neutrons ripped into a spray of fundamental particles. Finally, even those cannot hold together as space-time itself is dragged to infinite expansion rate in a finite time. The machine of physics hits a wall, and the strangest part is, current observations do not rule this out. Our measurements of W are consistent with a cosmological constant, but they still leave a gap where W could be less than -1. The Big Rip is not a prediction. It is a live option in the parameter space of the universe. If you are new here, pour yourself something warm because it gets worse. Being torn apart is only one way for everything to end. There is an even colder possibility that the universe does not just change speed, it changes the rules. Everywhere, all at once, with no warning at all. We will get to that. Alternative endings. 2. Vacuum decay. The ultimate cosmic ambush. So here is the thing. The universe might not just end by cooling or by tearing itself apart. It might end because the vacuum itself decides it has had enough. Not the air in your room, the vacuum. The thing we call empty space that every field, every particle, every machine and galaxy is built on. In quantum field theory, what you and I call empty space is more like a landscape of energy. Picture a ball resting in a shallow valley. It looks stable. It can sit there for trillions of years. But somewhere else on that landscape, there might be a deeper valley, a lower energy state. Our vacuum, the one defining your atoms and my narration right now, could be metastable. Not the true minimum, just good enough for the moment. If that is the case, then in principle, the universe has a way out. Quantum tunneling. A purely quantum move where the ball does not roll over the hill. It appears on the other side. Translating that into reality, at some random point in space, a tiny region could tunnel into the true vacuum, the deeper valley, creating a bubble with different energy, different rules, a different version of physics. And the strangest part is not that this can happen. The strangest part is what happens next. That bubble does not just sit there like a cosmic snow globe. The energy difference between our vacuum and the true one drives the bubble wall outward at nearly the speed of light. Not 10% of light speed, not 90%. Essentially as fast as causality allows. Imagine the worst software update you have ever experienced. Now delete the progress bar, the "Are you sure" dialogue, the release notes. Vacuum decay is the software update from hell. As the bubble sweeps through, it overwrites the operating system of reality, particle masses, interaction strengths, the whole quantum rulebook. Electrons might not exist in the same way. Protons might become unstable. Chemistry, as a concept, could fail. Let that sit for a moment. Every star, every planet, every classical memory stored on any hard drive, every qubit in every future quantum computer, all recompiled into a new physics where none of those structures can survive. There is no dramatic explosion, no lingering ash, just a different computation running on the same underlying space-time, with no place in it for you or me. And there is no warning. Because the bubble wall moves at near light speed, you never see it coming. No telescope could spot it in advance. One instant, the cosmic microwave background hums at 2.7 Kelvin. Your heart is beating. Your browser has too many tabs open. The next instant, those concepts are not even definable. Pattern interrupt. Exhale. This is a real scenario in our equations, and the Higgs potential we have measured makes a metastable vacuum look disturbingly plausible. But the computed lifetimes are absurdly long, far beyond the current age of the universe. If vacuum decay is on the schedule, it is on a page of the timeline we will never reach. Still, the fact that reality can, in principle, rewrite its own ground rules raises a deeper question. If the vacuum is negotiable, what else is? In the next section, we will leave catastrophic endings behind for a moment and ask what this whole story says about meaning in a universe that can change its mind. Alternative endings. Big crunches, bounces, and cycles. So if the vacuum can renegotiate the rules, you have to ask, what if the entire expansion of the universe is up for renegotiation too? What if the timeline we just mapped is not a straight line, but one loop of a much larger machine? Here is the thing. All of our talk about heat death and fading galaxies assumes that expansion just keeps going, driven by dark energy that behaves the same way forever. But roll the cosmic parameters a little differently, and the story flips. If the average density of matter and energy were higher, or if dark energy changed sign and began to pull instead of push, expansion could stall, slow, stop, reverse. In that big crunch scenario, the movie of the universe runs backward. Galaxies that spent tens of billions of years drifting apart would start to fall toward one another. Clusters would merge. The night sky would brighten as everything crowds back in. Not 10 trillion years, not 100 trillion years, but an ever-accelerating rush toward a final convergence. As space contracts, temperatures rise. Background radiation blue shifts from cold microwave hiss to white-hot glare. Black holes, which once quietly evaporated over unimaginable timescales, would instead gorge on infalling matter. The gap between atoms collapses. Cores of stars, then nuclei, then even protons are squeezed. In the last fractions of a second, all matter and radiation could be compressed into an incredibly dense, hot state, eerily reminiscent of the early universe. In a sense, it was the beginning, replayed at the end. Now, you could stop there and call that the final page. One colossal bang at the start, one catastrophic crunch at the finish. Lights out. But many physicists looked at that symmetric picture and thought, really, time just hits a wall. So they started to push on the wall. Enter bouncing and cyclic models. In loop quantum cosmology, the quantum structure of space-time itself acts like a pressure valve. When densities approach the Planck scale, gravity turns repulsive, preventing a true singularity and turning a would-be crunch into a bounce. One universe collapses, hits a minimum size, and then expands again with a new Big Bang as the rebound. Old aeon, new aeon. Same underlying quantum machine, doing another round of computation. Roger Penrose goes even further. In his conformal cyclic cosmology, the ultra-late universe after heat death, no matter, only very low energy radiation, can be mathematically squashed so that its end looks like a new beginning. One aeon's infinite future is glued to the next aeon's Big Bang. Time does not have a true start or finish. It is an endless relay race of universes handing the baton forward. Pour yourself something warm and let that sit for a moment. If any of these models are right, then the Big Bang was not the beginning of reality, only the beginning of this chapter. No absolute origin, No final ending, just an eternal sequence of expansions, contractions, and reboots. And the strangest part is not the mechanics. The strangest part is what this does to our sense of time and meaning. If the universe ends in a whimper, a bang, or a reboot, what does that say about the reality we inhabit now and about our brief, bright moment in between? We will get to that. Part 5. What time really is, from cosmic arrows to illusions. So this is where the timeline stops being just a list and turns into a question. We have a beginning, we might have an end. The mystery now is what that entire arc is telling you and me about time itself. Call this part 5, the meaning of the timeline. Up to now, we have been tour guides, Planck era, inflation, first stars, black holes, heat death, maybe a big rip reboot, dates, phases, transitions. But a universe with a low entropy beginning and a high entropy future is not just a calendar. It is a machine that manufactures an arrow. Here is the thing. The microscopic laws we know best, the quantum and classical equations you learn in textbooks, are almost perfectly time-symmetric. Run them forward, you get one result. Flip the sign of time and run them backward, you get another valid solution. The equations do not care which way you press play, you do. I do. Eggs break, they do not unbreak. Stars burn hydrogen into helium. They do not spontaneously reassemble pristine fuel. Your hard drive fragments, your coffee cools, your room gets messy unless you wage a daily war against it. That one-way drift is entropy increasing, and that is what we call the thermodynamic arrow of time. Stop and think about what that means in everyday terms. Every memory you have is a record written by some irreversible process. Neurons changing, photons scattering, energy dispersing. If those processes ran backward, your memories would erase themselves as neatly as they formed. The difference between past and future for you is the direction in which information becomes scrambled. So why was there ever order to lose? This is where the past hypothesis walks in. The idea is almost offensively simple. The universe started in an absurdly low entropy state, not just dense and hot, but exquisitely organized compared to what it could have been. Let that sit for a moment. Out of all the ways energy and matter could have been arranged, the initial condition picked one of the rare configurations from which entropy could climb for billions of years. In a sense, it was a cosmic loaded die. From that single special boundary condition, the thermodynamic arrow, the psychological arrow, and even the cosmological arrow of expansion all line up. Time feels like it flows because the universe is relaxing from that initial constraint. And the strangest part is that some approaches to quantum gravity hint that time itself might not be fundamental at all. In certain equations, the universe is described by a static wave function. Change appears only when you carve out subsystems and compare them. Time, in that view, is an emergent bookkeeping trick rising from correlations inside a deeper, timeless computation. If that is right, then the arrow of time might be nothing more than a side effect of boundary conditions at the beginning, and maybe at the end. Our sense of flow, of aging, of history, could be the way finite creatures experience a global story written all at once. So what happens to meaning if the flow is an illusion, but the arrow is real? We will get to that next. Block universes and branching realities. How many histories exist? If the whole timeline can be written at once, then there is a brutal follow-up question. What if it already is? Not in a poetic sense, in a literal, geometrical way. Here is the thing. In Einstein's relativity, the universe is not a movie that plays. It is the entire film reel laid out on the table. Past, present, and future are all points in a four-dimensional space-time block. Your birth, the death of the last star, the moment you hit like and subscribe if you are new here. They all coexist as different locations in this frozen structure. What you and I call now is just a moving spotlight sliding along the reel, not a special frame built into the machine of reality. Stop and think about the difference. In your day-to-day experience, time flows. You make choices, results unfold, the story advances. But in a block universe, that flow is not an extra ingredient of physics. It is a way a particular kind of brain reads a timeless record. In a sense, it was always true that you would watch this sentence, because that event is just one coordinate in the block. And the strangest part is, quantum theory takes this already uncomfortable picture and twists the knife. One radical reading of the equations, the many worlds interpretation, says the global wave function never collapses. Every quantum event that could have multiple outcomes does not pick one. It branches. The universe splits into non-communicating copies, each carrying a different result, all equally real in the mathematics. A single radioactive atom. In one branch it decays, in another it waits. A primordial quantum fluctuation in the early universe. In one branch it seeds a galaxy here, in another it nudges matter there, in another it never grows at all. Let that sit for a moment. The same underlying laws, the same quantum computation humming along, but an ever-thickening forest of parallel histories. Which means the grand cosmic timeline we have been walking through together is, on this view, just one path through an unimaginably dense multiverse. There are branches where inflation ended a bit earlier, where the Planck-era foam froze into different patterns, where dark matter clustered into different galaxies, where no stable stars formed and no chemistry ever got off the ground. There are branches where Earth never congealed, where life flickered and failed, where you never existed to wonder about any of this. Pattern interrupt, zoom out. Do not picture the heat death of one universe. Picture a vast ensemble of block universes, each with its own beginning, middle, and end, each running its course toward thin, cold equilibrium. In some, black holes evaporate into silence. In others, vacuum decay rewrites the rules halfway through the story. All of them written, all of them already there in the block. So if there are countless completed histories, what does it mean to live one moment well? In the next section, we will push directly on that question. The cosmic computer. Is the universe doing a calculation? So here is one brutal answer to that question. To live one moment well is to update the universe. Every breath you take, every neuron that fires, is a microscopic step in a cosmic computation that has been running since the Big Bang. If you are new here, pour yourself something warm, because this is where the story gets uncomfortably close. Physicists like John Wheeler and Seth Lloyd have argued that the universe is not just described by mathematics. In a sense, it was, and is, a machine doing math. Every interaction, every collision of particles, every quantum measurement is a logic operation. The state of reality at one moment is the input. The next moment is the output. Information, in this view, is not an abstract idea living in our laptops. It is encoded in the exact arrangement of particles and fields, in the quantum amplitudes smeared across Hilbert space. The pattern of photons in the cosmic microwave background is a fossil record of ancient bits, written when the universe was only 380,000 years old. Your DNA is another record, a compressed archive of 4 billion years of biochemical computation on Earth. Run that forward, from the Planck era, when space-time itself flickered like quantum foam, through inflation, star formation, galaxies, black holes, all the way to heat death. You can treat the whole timeline as one vast, irreversible calculation. Entropy is not just disorder, it is the log of how many microscopic configurations the universe has already counted through to arrive at its current macro state. Let that sit for a moment. But this is not an all-powerful supercomputer. The laws of physics impose hard limits on what can be computed. Nothing can signal faster than light, which means there is a maximum rate at which distant regions can coordinate their part of the calculation. Quantum uncertainty says you can never squeeze both position and momentum into perfect precision, so no classical-style infinite precision arithmetic. And whenever a machine, cosmic or human, erases a bit, Landauer's principle demands a price in heat. That is why real computation warms your laptop, and why, at a deep level, thinking is thermodynamically expensive. So if the universe is computing, what is the output? Is it simply the next frame of its own movie, each state deterministically or probabilistically generating the next? Or is the real result the exploration of all possible configurations consistent with its laws, a systematic survey of what can exist given these particular rules and no others? And the strangest part is, you and I are inside the machine. Your mind is a subroutine running on wet neural hardware, which is running on quantum fields, which are running on the cosmic code. If that is true, what does it say about consciousness, about meaning, about the value of a fleeting moment that is, from the universe's perspective, just one more line of output? We will get to that. Consciousness in a mortal cosmos. Why our moment matters. So here we are, a tiny process running inside the cosmic machine, staring at a timeline that stretches from 10^43 seconds after the beginning to something like 10 of 100 years into the dark. Not 10 years, not 100 years. A 1 followed by 100 zeros. Next to that, an 80-year human life looks almost offensively small. You get maybe 2.5 billion heartbeats, a few thousand weeks, then nothing. Against a universe that survived inflation, built galaxies, forged heavy elements in stars, and will one day watch the last black hole evaporate. Your Tuesday afternoon meeting does not look like a major event. Let that sit for a moment. This is the existential vertigo. You zoom out, the scale explodes, and your own timeline collapses into a pixel. And the strangest part is, the more precisely physicists map the cosmic arc, from the Planck era to heat death, the easier it is to feel like you are just a numerical rounding error in someone else's computation. Here is the thing. Rarity is value. In physics, in art, in your life. Diamonds are valuable because they are hard to arrange, not because the universe loves carbon. A perfectly timed joke, a once-in-a-lifetime eclipse, a fragile quantum state in a lab that survives for a few microseconds before decohering. What makes them precious is that they are improbable under the normal flow of reality. Your conscious experience is like that. For you to be having this exact moment, the universe had to expand at just the right rate, cool to the right temperature, form stars, cook heavier elements, build planets with liquid water, and then run 4 billion years of blind biochemical computation on Earth without wiping the slate completely clean. Against the backdrop of all possible universes, that is an outrageous, statistically insane result. This is where the anthropic principle sneaks in. You observe a universe compatible with your existence, because if it weren't, you wouldn't be here to ask. In a sense, it was inevitable that any observer would find themselves in a just right cosmos. That sounds comforting, like the rules were tuned for you. It also feels unsettling, like discovering the only reason the room has oxygen is that all the people who walked into vacuum died before they could complain. But meaning does not require eternity. A song is powerful because it ends. A story with no final chapter is not profound. It is broken. If the universe really does have a finite narrative arc, from quantum foam to heat death, then your life is not outside that story. It is one of the sentences where the plot briefly becomes self-aware. Pattern interrupt. Pull your attention away from 10-100 years and into the next 10 seconds. Feel the weight of your body wherever you are sitting or standing. Notice the temperature of the air on your skin, the way your eyes are tracking these words, the tiny muscular adjustments keeping you upright. This is classical, ordinary, almost boring. And yet it is also a quantum miracle of coordinated matter, a local pocket where the universe is not just expanding, it is noticing. From the outside, you are a flicker. From the inside, this flicker is all of reality, right now. That difference is not a bug, it is the gap where meaning lives. And if consciousness really is the rarest phase the cosmos has ever produced, then what we choose to do with our brief window might be the most consequential line of code the the universe ever runs. We will get to that, because the next question is brutal. If the universe is writing a story, who, if anyone, is the author? Are we early or late? The cosmic timing paradox. If the universe is running a story, then the next twist is uncomfortable. We have to ask where in the timeline we actually walked on stage. Are we the opening act, or are we showing up right before the lights go out? Here is the thing. We live about 13.8 billion years after the beginning, in a universe that, according to our best equations, can keep expanding and forming low-mass stars for trillions of years. Not 10 billion, not 100 billion, trillions. Let that sit for a moment. If the show can run 1,000 times longer than it already has, what are the odds that you and I just happen to exist in the first tiny sliver? One camp says that is exactly what is happening, and that we are early. Star formation in the universe peaked around 10 billion years ago and has been declining ever since. The raw fuel for new suns and new planets is getting used up or locked away. Heavy elements, the ones you need for rocky planets, oceans, and nervous systems, were forged in generations of massive stars that have mostly already lived and died. On this view, the cosmos has already passed its most creative phase. The galaxies are like aging cities where the cranes have come down and the big building projects are over. In that picture, future habitable environments look different and rarer. You might get long-lived red dwarf systems, but with brutal flares, tidal locking, and strange climate regimes. Maybe the sweet, Earth-like window we enjoy now is a brief, front-loaded anomaly, and complex life is something the universe tried early, once, in a narrow band of cosmic time. But then there is the opposite argument, which flips the script completely. Red dwarfs, those tiny cool stars that look unimpressive in every Hubble image, can burn for up to 10 trillion years. They are the slow, efficient machines of the galaxy. Most of the planets that will ever orbit them have not even formed yet. If those worlds can host life and minds, then the overwhelming majority of potential observers are not just in the future, they are deep in the future. In a sense, it was arrogant to assume we are typical now. This is where the doomsday argument and observer selection effects sneak in. They treat you as a random draw from all observers who will ever exist and then ask, what does your birth rank say about how long the story runs? If we are early, maybe that means the window for civilizations is short. If we are late, maybe the universe, or our technological phase, is already far along toward its endgame. None of these inferences are airtight, and the strangest part is how much hinges on what we do not yet know about life elsewhere. Yet there is one way in which we are undeniably special in time, and it has nothing to do with philosophy. Right now, we can still see the cosmic past. The cosmic microwave background still glows. Distant galaxies still sit inside our horizon. Give the expansion a few 100 billion years, and that fossil light redshifts into oblivion. Other galaxies accelerate away faster than light, and the observable universe collapses to a lonely island of local stars. Future astronomers under those red dwarfs will look up and see almost nothing. So whether we are early or late on some abstract probability curve, we are living in the only era when the universe lets its full history be visible. We are the brief moment when the machine not only runs, but can read its own source code. And we will get to that, because the next step is to ask what happens when even the code starts to decay. The long, cold future after the last star dies. The vanishing past, cosmic horizons and lost galaxies. But even as the code decays, the machine keeps running. And the strangest part is that the longer it runs, the less of its own past it can ever access again. Here is the thing. In an accelerating universe, there is a hard limit on how much of reality can ever talk to you. Not a practical limit, a fundamental one. Cosmologists call it a cosmic event horizon, and it is not a metaphor. It is a literal boundary in space-time. Cross it, and no signal, no photon, no clever quantum trick can ever reach us, no matter how long we wait. Pour yourself something warm and let that sit for a moment. We are used to horizons being temporary. Sail far enough, you see new land. Build a bigger telescope, you see fainter galaxies. That is how classical intuition works. More effort, more data. But dark energy changes the rule. As expansion accelerates, distant galaxies are carried away faster than their light can outrun the swelling fabric of space. At some point, their last photons aimed in our direction are stretched, red-shifted, and thinned out until they are effectively erased from our sky. Not 10 years, not 100 years, not even the age of the universe now. We are talking trillions of years of cosmic computation, during which more and more galaxies slip over that horizon. First, they fade to infrared ghosts, then to radio whispers, then to nothing at all. The result is not just a dimmer night, it is a shrinking archive. Entire chapters of the early universe's story are physically removed from the list of questions any future observer can ask. Fast forward a few trillion years. Imagine an astronomer in a quiet remnant of what was once the local group, long after the Milky Way and Andromeda have merged into a single swollen galaxy. Outside that island, black, no other galaxies, no Hubble expansion to measure. The cosmic microwave background, which for us is a bright fossil from 380,000 years after the beginning, has been stretched to wavelengths larger than the observable universe itself. Their detectors see nothing. From their perspective, there is no evidence of a hot Big Bang at all. If you are new here, that should feel almost impossible. Same universe, totally different accessible reality. In a sense, it was always like this. What you can know is limited by where and when you are. But dark energy makes the gap brutal. We live in a brief era when the CMB is still visible, when galaxies still crowd our horizon, when we can measure expansion and reconstruct an origin story with absurd precision. And here is the real twist. The universe's timeline is not just a sequence of physical events. It is a schedule for which questions can exist. Some questions can only be asked now by creatures with this vantage point. So what happens when the questions themselves start to die out? We will get to that, because the next phase is even stranger. A universe where not only the past, but meaning itself begins to evaporate. The universe's secret, what the full timeline is trying to tell us. Meaning evaporates, questions thin out, the universe heads for silence. But if you zoom all the way out, from the first quantum flicker to that last fading photon, there is a pattern hidden in the timeline itself. And it is not a gentle one. We started with almost nothing, a Planck-scale haze where space-time wasn't a stage yet, just quantum foam flickering in and out of existence. Then inflation hit, blowing that foam up faster than light, ironing tiny fluctuations into the seeds of everything. Not 10 years, not a billion years. 43 seconds to go from undefined to primed. Let that sit for a moment. From there, the story slowed down. Atoms formed. The first stars lit up, forging heavier elements in their cores. Galaxies assembled, black holes grew, planets cooled, chemistry got weird, and on at least one world, a brain looked up and named the whole machine universe. You and I are living in that strange, narrow middle, between a low entropy beginning and a high entropy end. Here is the thing. That shape, smooth start, structured middle, empty finish, does not look fundamental. It looks like the behavior of an emergent process, the way a computation runs from simple input through messy intermediate states to a boring stable result. In a sense, it was. The Big Bang is like the initialization step, the heat death is the output, and everything in between is the universe chewing through its own code. Stop and think about the difference in scales that code has to span, from 10 more round to 35 meters of quantum foam to 10 more 26 meters of cosmic web, from 10 more round more 43 seconds to 10 more Google years. A classical simulation of that range is impossible in any machine we could ever build, and yet reality does it natively, effortlessly, as if the timeline is just one particular run of a deeper program. And the strangest part is not that this looks like computation. The strangest part is that, for a brief window, the computation became self-referential. consciousness appears, and suddenly the universe is not just evolving, it is modeling itself. Neurons, little wet quantum-adjacent processes, encode galaxies, black holes, heat death scenarios. The code is reading its own source. Pattern interrupt. What if that is the whole point of the middle? Not moral purpose, not a cosmic mission, but a structural role. Low entropy at the start allows complexity. Complexity allows observers. Observers allow the universe to form internal representations of its own trajectory before the gradients flatten out and the questions stop. If you are new here, this is the moment where most videos would give you a neat answer. Here, we get something else. A question the universe is asking through you. What does it mean for a finite mind, running for a few decades on a damp ball of rock, to partially understand 13.8 billion years behind and untold trillions ahead? We will get to one more twist, because this might not be the only run of the program. From first flicker to final fade, your place in the story. So let's zoom out one last time and actually answer that question the universe is asking through you. Because you have not just been watching this story, you have been traveling through it. We started before time had a name, at the edge of the Planck era, where our equations fall apart and space itself flickers like quantum foam. We watched inflation tear a pinprick of vacuum into a cosmos. We saw the first light, that baby picture glow of the cosmic microwave background, when the universe was 380,000 years old and still learning how to be transparent. We followed hydrogen clouds collapsing into the first stars, stars into galaxies, galaxies into a web of structure stitched together by dark matter. We watched those stars cook heavier elements, explode, seed new systems. We dropped in on a small yellow star, on a wet rock, where chemistry kept trying combinations until one of them woke up and started asking questions. Here is the thing, that whole timeline is not just outside you, it is in you. Every proton in every atom in your body rode that expansion from the Big Bang. The carbon in your cells was forged in the core of some long-dead star. The iron in your blood is the cooled ash of a supernova. In a sense, it was inevitable that matter would end up making something that could look back and notice. And right now, that something is you. Let that sit for a moment. The same universe that will, in the far future, let the last star burn out, that will hand the stage over to black holes, and then to a thin quantum fog of particles, has, for a brief window, arranged itself into eyes and hands and minds, into commutes and emails and late-night walks, into you on this particular night, watching a video about the entire history of reality. And the strangest part is how fragile this window is. We live in a universe still bright enough for life to feed on starlight, still transparent enough that photons from the early cosmos can cross billions of light years and end up in our telescopes, letting us literally see 13.8 billion years into the past. Still young enough that there is oxygen in the air, liquid water on the ground, and bandwidth left in your brain to wonder what it all means. That will not always be true. There is a future where the night sky goes blank, where the cosmic microwave background redshifts into oblivion, where even memory of the beginning becomes impossible because there is nothing left that can remember. So what do you do with a Tuesday morning in a universe like that? You live it, but with the volume turned up on context. Your coffee is water that condensed from ancient interstellar ice. Your arguments and jokes and text messages are quantum excitations in a brain that is, for a few decades, beating the odds against entropy. The gap between taking out the trash and contemplating heat death feels huge. In reality, it is the same story, just at different zoom levels. If you are new here, this is the tension we live with. You are one small configuration in a vast machine, and yet the only place the universe can feel like anything at all is inside configurations like you. If that resonates, if you like living in that space between cosmic insignificance and personal meaning, you are not alone. There is a community here that keeps asking these questions together. We will get to that in a moment. Stay for the next chapter. What we still don't know. We will get to that in a moment because there is an even stranger tension sitting underneath everything we have just walked through. We have told a clean story. Planck era, inflation, stars, black holes, heat death. But here is the thing. The closer you look at that timeline, the more it starts to fray at the edges. We do not actually know what happened in the Planck era. At around 10 to the minus 43 seconds, our equations just stop. General relativity and quantum mechanics refuse to cooperate. Space-time might have been a quantum foam. It might have tunneled out of nothing. It might have bounced from a previous universe. Every option sounds impossible, and yet one of them is the real opening move of your reality. Let that sit for a moment. The same ignorance lives at the other end. We draw these elegant curves for dark energy and say the universe will accelerate forever, or rip itself apart, or tunnel into a lower energy vacuum and erase everything at the speed of light. The data we have now fits multiple endings. Heat death, big rip, vacuum decay. They are not competing YouTube thumbnails. They are mutually exclusive fates, and we do not yet know which one the machine is actually running. And in between, 95% of the universe is dark matter and dark energy, which is a polite way of saying we see their gravity but have no idea what they are. Is dark matter a new particle, a whole dark sector with its own forces, or a sign that our picture of gravity is wrong? Does dark energy come from quantum fields, or from the geometry of space-time itself? These are not footnotes, they are gaping holes in the story. That uncertainty is where the next episodes live. If you are new here, this channel is a recurring space to sit with those gaps and push on them. Quantum gravity and the beginning. Deep dives into dark energy and the possible ends of time. Black hole information, and whether the universe is secretly a gigantic error-correcting code. The multiverse, and what it would actually mean if our entire observable bubble is just one branch in a much larger computation. If you want more late-night journeys through that territory, hit like and subscribe. Share this with the one friend who will text you angry questions at 2 a.m. and pour yourself something warm the next time we upload. And I do want your questions. Not just for engagement metrics, but because the best episodes on this channel have come from comments that said, "Wait, go back, what about this?" Tell me which ending scares you, which beginning confuses you, which part of the cosmic clock feels wrong. That feedback is how we decide what to simulate next. Pattern interrupt for you, right now. Before you let the algorithm drag you into the next video, pause. If you can, step outside and look at the sky. If you cannot, just close your eyes and picture the entire timeline we just walked. From a quantum flicker at the Planck scale to a universe faded into near nothing. Feel the difference between those scales and the few decades you get. And the strangest part is, that tiny human window is exactly where the universe has learned to ask what it is. When you are ready to keep asking, the next chapter will be waiting. The last word before the last star. So here is the thing. The universe will keep going long after the last human name is forgotten. Long after the last star burns out, cools, and crumbles into the dark. But for one thin, ridiculous interval on that timeline, you and I are here. Right now. On a small rock orbiting an ordinary star in a galaxy that will not remember us, we get to be the part of the universe that knows it has a past and can imagine a future. Let that sit for a moment. From the Planck era, when time itself was a quantum experiment, to the black hole epoch, when even protons may decay, almost everything that has happened has been automatic. No committee, no plan. Just physics, running its computation on a vast, expanding stage. You are an exception to that. Consciousness is the result that does not have to be there, and yet somehow is. That is the only gap in this entire cosmic story where choice appears. We cannot edit the Big Bang. We cannot rewrite the heat death. But in between, in these few fleeting centuries of technological civilization, we can edit how we treat each other. We can decide whether this planet ends as a thriving oasis or a cautionary tale etched into a thin layer of fossil fuel and plastic. We can choose whether our machines amplify wisdom or just accelerate distraction. In a sense, it was always going to be like this: a quantum universe that mostly behaves like a classical machine, with tiny pockets of freedom carved out by complex chemistry and nervous systems. The difference is that now you know that 95% of everything is dark, that stars are temporary, that even black holes evaporate. And once you know that, pretending your choices do not matter is no longer an honest option. So the invitation is to carry a double vision. On one side, humility. You are small, fragile, and brief on scales that run from 10 grams and 43 seconds to 10 Google years. On the other side, responsibility. You are a conscious pattern in a universe that almost never wakes up, with the power to reduce suffering, to steward a biosphere, to push understanding forward a few more steps. If you are new here, this is what this channel is for: to take the infinite and drag it right up against your next decision, to use the strangest parts of modern physics as a mirror for how you live tomorrow morning. So thank you for spending a slice of your finite time on this exploration of the infinite with me. You could have been anywhere else in reality, and you chose to be here, thinking about the fate of all things. I do not take that lightly. If you want to keep going down this tunnel with me, hit like and subscribe, pour yourself something warm, and come back for the next deep dive into the strange, beautiful, and terrifying universe we inhabit. Until then, take care of yourself, take care of each other, and remember, for now, you are the way the universe looks back at itself.